Okay. So the recording has started. Okay. So again, in hydraulics, right, I will focus more on specific energy and the profile sketching, but I will still cover everything. I will just spend the most time on energy and drawing. So, I mean, we see later lah. But basically, this is everything that you need to study. Okay, so let's start with uniform flow. So I won't be covering too much. I mean, okay, so basically what you need to know from uniform flow, right, is the flow that happens when there are no obstructions in channel flow. This will be clear when I explain the water profile sketching, but for now, just take it as it is. So it's basically how water is supposed to flow given the channel slope and channel roughness. There are only a few equations that you need to remember from uniform flow. The first one is discharge. This is the classic. Please don't forget this. The second one is Manning's equation. This is to find the normal depth, so yn. The last one is hydraulic radius. Hydraulic radius is area divided by wetted perimeter. Basically, don't forget that P is wetted perimeter. So basically, it's saying that it's the one in contact with water. So the perimeter is only this one. It does not include this side. It's only the one in contact with water. Okay. And then another thing that you need to know from uniform flow is that for wide channels, the hydraulic radius is approximately the normal depth. That's the only thing you need to know from uniform flow. Okay. There's another thing actually that you need to know from, but this is a bit beyond. But anyways, you need to know the terms supercritical, critical, and subcritical flow. So supercritical flow is the flow which is shallow and fast. So the depth is below the critical depth. I will explain this later. Critical flow is the depth which is equals to the critical depth, and the subcritical flow is the one which is slow and deep. So yeah, that's everything for normal flow. We won't go to questions first because usually this is combined with specific energy. So yeah, this is everything that you need to know from uniform flow. So we're done. Let's go to the next chapter, which is the specific energy. So again, I will just give you a very brief review. So for specific energy, this is the general equation. So this is the general equation. So for any channel, the specific energy is V squared over 2G plus Y. Okay. And then we have critical conditions, which is this. This is usually given, I think, so you don't need to memorize, but just know that this exists. Okay. The next thing is rectangular channel. So wait, before that, I just want to clarify. V is velocity, E is specific energy, and Y is channel depth. Okay. This is different from water level. This is not water level. You'll see why later. But anyways, remember that this is channel depth, not water level. Okay. So usually, right, in this module, we are only interested in rectangular channels. Sometimes you are asked non-rectangular channels, but mostly rectangular. So for rectangular, right, you can replace the V. Okay, V is Q over A, right? So we can replace, but then big Q, okay, sorry, small q is Q over Y. So you can replace this equation with this for rectangular channels. So this is the first equation that you need to memorize. Like, not memorize, familiarize. Okay. So so when you plot this, right, when you plot the specific energy of a rectangular channel, you will have this diagram. So some things to take note. First thing first, one value of Q corresponds to one curve. So let's say Q equals 3. Let's say this is Q equals 3. So that's the only curve, okay? I mean, like, that's the curve for Q equals 3. Let's say you have Q equals 5. Q equals 5 will correspond to, let's say, another curve. Let's say this one. So 1Q, 1 curve, okay? 1Q, 1 curve. The next thing that you need to know, right? For each value of specific energy, there are 2 depths. So one value of energy, let's say 2.5. No, let's say 2, let's say 2. So one value of energy two depths. The first depth is very deep. See, the first one is deep. This is the one that I told you just now in the uniform flow. This is the subcritical. So this depth is subcritical. The other depth is supercritical. So this is the second thing that you need to know. 1E, there are two depths. So when you solve for, let's say you have the energy, right? You want to solve for depth. You will have two answers. Yeah, the first one is subcritical. The second one is supercritical. I will tell you how to choose which one to use in like after this. Yeah, just stay tuned. For now, just accept that for one energy, two depths. Okay, so one Q, one curve, one energy, two depths. The next thing that you need to know, for one curve, we have a minimum value. This is called the critical condition. Okay, this is called the critical condition. So because one Q have one curve and one curve have one critical condition, then it means that for one Q, there's one critical depth, which is related to this equation. So again, this is the so this is the first thing that you need to know, the first equation. This is the second equation that you need to know, the critical depth. So finding critical depth from Q. The third equation that you need to know is this one. So this relates the critical energy with the critical depth. So this is the critical energy. This is the critical depth. Okay. So far so clear. Am I talking too fast? I'm trying to rush because we still have like questions. But basically, these are the three equations that you need to know. Okay. Next up, we go to humps and depressions. So sorry. So for humps, right? Logically, if you can think of hump as you need energy to climb the mountain. Okay, you need energy to climb the mountain. So of course there will be a drop in your energy. So let's say your energy starts with E1. You want to climb the mount. You want to climb the mountain delta Z. Then you need to pay by how much? By delta Z. So if you see in the diagram on the right, this is E1. It goes down to E2. Okay, and you see in this case the depth drops. Okay, the water depth. The opposite is true for depressions. In this case, right, you will gain energy. So you start from this line, you'll end at this line. Okay. Just take note that Q stays. So as in like the curve doesn't change. Okay, the curve doesn't change. The energy changes. This is for humps and depressions. Okay. There are some rules for humps and depressions. The first one is flow accessibility. So let's say you have a hump, right? You have a hump. So look at this left diagram. So let's say you are starting with this energy, and then you have a hump this much delta Z. So you'll end up with E2. Okay. So the first rule that you need to know is the flow accessibility. It's basically saying if you start with supercritical, end with supercritical. You cannot start with supercritical and end with sub. Cannot, okay? Cannot. If you start with super, end with super. If you start with sub, end with sub. Okay? That's, oh, sorry. Okay, so that's the first rule that you need to follow. So, okay, I mean, it will be clear when we do the question, but keep in mind, okay? Keep in mind. Second thing is choking. So what happens when, let's say you have energy, right? The hump is very high to the point that the drop in energy is very big. So your second energy drops below the energy which is critical. In this case, there will be choking. So what happens in choking? So instead of dropping below the energy critical, the second energy will be stuck at critical, and the energy in the beginning will increase to compensate the hump. So before, like E1 is this red line, right? So okay, this red line, this is E1, right? So this thing, because the hump is too big, right? So the second energy will stuck in this line. So this first energy will go back. Okay, go back by how much? You calculate from the critical energy. From critical energy, it goes back by delta Z. This is choking. Okay, I mean, okay, the exact term is ponding actually. Choking and ponding. Choking is exactly at critical. Ponding is the one that causes E1 to go back. So this is ponding. But anyways, yeah, so just keep in mind that if choking happens, E2 becomes E critical, E1 increases to critical plus delta Z. Okay, so that's for humps and depressions. Lastly, for specific energy, we have expansions and contractions. So, so for expansions and contractions, energy stays, Q changes. Okay, so for humps, right, the Q stays, the energy changes. For contractions and expansions, it's the other way around. Yeah. So for contraction, this graph will go to the right. Okay. So if you notice, right, energy stays. So the change in depth is caused by the shift in the graph. So if you see, this is Y1, this is Y2, there's a slight drop. Okay. So this is for contraction. Expansion is just the other way around. Okay. So again, I'll repeat. For humps and depressions, energy changes. For expansions and contractions, energy stays, Q changes. So the graph shifts. Okay. Flow accessibility still applies, as in like if you start with subcritical, you end with subcritical. You cannot start with subcritical and end with super. Cannot. Okay, cannot. Sub to sub, super to super. The second thing is there can be choking for contractions, but the way it chokes differently. Okay, so the way there's choking, but the system is different. It's not like this. Okay, for expansion and contractions, the how they choke is like this. Sorry, only for contraction. Only for contraction. So how to choke a flow in contraction? Remember that our graph, right, shifts to the right. So choke happens when the graph shifts to the right to the point that it's like beyond our first energy. So let's say you have Q1, right? And let's say like you stuck here. Well, it's fine because you have this depth, okay? But then if you keep pushing, like keep pushing the new graph beyond the E1, then there will be choking. So how does this choke? Well, the first energy will increase, okay? So supposedly contraction and expansions, the energy stays. But if there's choking, then the energy will go along with the new graph, okay? So E1 will increase to this the new graph's critical condition, okay? So this will move there together with the graph if there's choking. So far so clear. That's everything for specific energy. So anyone wants to ask? Anyone wants to ask to any of the concepts from expansions and humps? I'll give you 10 seconds if nobody answers. Okay, choking from contraction. Um, as in like, let's say you have, let's say you have this graph, right? This graph, okay, and then this is your energy. Sorry, this is your energy. This blue line is your energy. Okay. Yeah, E changes if there's choking. If there's no choking, E stays. Okay, energy stays if there's no choking for contraction and expansion. Yeah. So like let's say, right, so Q increases when E changes. What do we look out for? How to explain it? Well, okay, never mind. I think this one is easier if we do the questions, I guess. Okay, okay. I think I'll elaborate this when we get. Okay, okay. Okay, Ken. I guess we'll start with the first question then. Okay, I think it's clear if we do the question. Okay, but just keep in mind all the stuff that I said. Okay, keep in mind. So let's start with this question. So this is a bit more of theory. So oh yeah, I've put like all the codes on top, so you guys can refer to the real past paper if you want. Okay, so let's go with the wait wait a second. Give me some time. Um, I'm opening my solution. Okay, okay. I mean, just in case I've done this, like I've done some questions from this actually. Okay, so let's start with this one. So with the aid of specific energy diagram, explain briefly one how choking and ponding happens in a hump. Secondly is why choking does not occur in the depressed section. Okay, so let's start very quickly. So this is exactly what I said before for the first part. So let's start with choking and ponding for a hump. Okay, this is for a hump. Okay, so this is Y, this is E, this is our diagram. Blah, okay, yeah. Okay, so choking and ponding. So let's start with choking. So choking happens. So this is our energy, right? Let's say this E1. Choking happens when the hump is exactly decreases E1 to the critical energy. Okay, so this is for choking only. So that's your answer actually. So choking decreases our initial energy exactly to the critical energy of the curve. Okay. Secondly, how about ponding? Ponding happens when the energy is decreased beyond the critical point. Okay. So this is our initial energy. Actually, I'll draw it with this line. So it is decreased beyond the critical energy. So there's ponding. If there's ponding, then we need to work backwards. We need to work backwards. So we start from the critical energy, which is this one. So our E2 will be stuck here. And our initial energy will be increased because it needs to compensate the hump. Yeah. So this E1, this E1 star. So the distance is exactly the you can think of this like a depth lah, basically. You can think of this as a depth. Yeah. So is there a difference between choking and ponding? Um Honestly, right, from the books that I read, they are the same thing. But from what the prof said, right, just follow the prof. Choking is like choking is you decrease the energy exactly at exactly at the critical condition. Ponding is the ponding is like the increase of the initial depth due to choking. So choking means like you decrease it to critical energy. Ponding means the increase of the initial energy. It's like okay, choking is decrease to EC. Ponding is the increase of E1 to E1 star. So this is choking and ponding. Yeah, so ponding is the one for like increase of E1 to E1 star. Yeah, so choking refers to the decrease in like decrease to EC. Ponding is in the increase of E1 to E1 star. Yeah. So I mean it's just terminology lah, but okay, but why not? Okay. So yeah, this is all that's it. So far so clear, right? This is exactly what I said. So choking means you decrease it directly exactly to the EC. Ponding means because the hump is too high, so it so like EZ is too high, so it's supposed to be this much, right? Cannot. So you instead, right, your final energy will be here. The initial energy will increase. Yeah. So I hope this is clear. Second question is why choking does not occur at depressed section? Well, you just draw the diagram again. This is Y, this is E. So why does not occur in depressed section? Because let's say this E1, if there's a depression, then our energy will be increasing. So this is like E2. So the reason there will be no choking if there's depression, because E2 will not reach EC. Because logically, right, if you start with E1, you increase the energy, then it won't go like to the nose, right? It will go the other way. So yeah. So no choking. So no choking for depression. Yeah, because energy will increase. It will not go to the nose. Okay, so is this clear? If this is clear, then I'll continue. Now this is the real deal, the one with the calculations. So okay, so you're given a wide channel, wide 8 meters, flow rate, bed slope, and Manning's coefficient. So you need to find the critical and uniform depth. So for uniform depth, I forgot in the lecture, did they use YO or YN? But in this case, I'll use YN. Yeah. So for uniform depth, you need to find via Manning's equation. So we have a rectangular section, wide channel actually. So from Manning's equation, you have Q equals 1 over N A RH 2 over 3S. Okay, since this is uniform flow, because we are interested in the normal depth, right, which is uniform flow, we can use SO. If the flow is not uniform, we need to use SF, the friction slope. Okay, but in this case, we can use the channel slope because it's uniform flow, to the power of half. Okay, so let's input the numbers. Wait, actually, let me draw the channel first. So this is white, right? So we have this is Y, and this is like 8, right? So let's just input the numbers. So Q is 16, 1 over N is 0.0136. A is 8 times Y. Hydraulic radius, since it's a wide channel, we can approximate it as YN. So this is what I'm saying from the one before. You just need to know that for wide channels, hydraulic radius is approximately Y. Okay. So Y. Actually, I'll just use this, this notation. So SO is 0.001 to the power of half. So you can solve for Y. Bringing out your calculators. So 16 times 0.0136 is 0.2176 is equals to 8. Okay, what's 8 times 0.001 to the power of half? Yeah, so we have this. So Y equals, let's solve for Y. So Y is equals to 0.2176 divided by that much, which is 0.86. Does everybody get the same answer? I hope so. Okay, so this is your normal depth. Done. Okay. Wait, this is what? 17, 18, 2B. I see. I'm just checking. Okay. Next we have, sorry, that's, oh yeah, GG. Sorry. Oh, okay. First mistake of the day, guys. First mistake of the day. So this is still to the power of 5 over 3. So Y equals to, this is to the power of 3 over 5. So let's do it. 0.91. Is it? Okay, so actually 0.2176. Let me check again. 0.25298. And to the power of 3 over 5. Yeah, 0.914. So if you see the solution, as in like, if you see the PYP solution, it really different. We get 0.914. The PYP solution has 1 meters, but it's fine because the PYP solution used the literal hydraulic radius. We are using the approximation. Yeah, but it's fine to use approximation because we have wide anyways. Okay, so uniform depth done. So let's find the critical depth. So YC. So YC, right? Again, I've told you before, for one Q, it always corresponds to one YC. So we need to find the Q first. So Q is, small q I mean, is Q over B, 16 divided by 8, 2. So we have YC is Q squared divided by G to the power of 1/3. So this is 2 squared to the power of divided by 9.81 to the power of 1/3. So calculators, we have 0.741, 742. Okay, so first question done. Oh, wait, never done, not done. We need to determine the type of slope. So type of slope, actually I haven't covered this, but I guess we can do it now. Why not? It's a bit, see, like hydraulic questions are always overlapping. So you really cannot divide it to to different chapters, I guess. But basically, right, because the y normal is bigger than the YC, right? Slope is mild. Okay, because yeah, type of slope. Slope is mild because normal flow is subcritical. As in, like, if you know, right? Let's say. So let's say you have y critical, right? If this is your normal flow, then this is mild. If this is your normal flow, which is below YC, it's supercritical. As in, like, logically, right? If you have a mild slope, it will go slowly, deeper and slowly. That's why if the y normal is above the critical, it's mild. If the y normal is below critical, it means like it's very fast, right? So it's steep. But in this case, we have mild. So yeah. So that's first question done. Let's go back. Suppose a broad crested weir is installed to measure the discharge. Calculate the height of the weir. So for this question, we need to know what does it mean by measuring the discharge. Logically, right? So this is the logic, okay? This is the logic. Remember that I told you 1Q corresponds to 1YC. Okay? Remember that 1Q corresponds to 1YC. Well, the reverse also applies. So if you know the critical depth, you can find the discharge. Okay. If you know one critical depth, you can find the discharge. So the logic, right? If you are going to install a broad crested weir to measure the discharge, you want the flow on the weir to be critical. Because if you know the critical, you know the discharge. So you get the logic, right? So in this case, right, the question is saying that the flow on top of the weir must be critical. So flow on weir, so flow above weir is critical. So what do we have? Wait, yeah. So logically, right, we have this is the weir. So initially we started with y normal, right? Then it will drop to y critical. Okay, actually it's like this. So there's M1 first, then okay. But anyways, this is like details later. Okay, okay. Let's say we have this. So so how do you find the critical depth? Well, remember that this is the delta z, right? Um, let's call this E1. Let's call this like E2, I guess. But E2 is EC, so EC because again we want critical, right? Because again we want the flow to be critical to measure the discharge. So yeah, so for this one, right? What should we do? Wait. Oh, GG, never mind. We found a critical depth, right? We found a critical depth. Um, Wait, I'm a bit lost. What did I do last time? uh, Shoot. Wait, why suddenly my head blank? How to find the height of the weir? Okay, so E1 equals E2 plus YC, right? Um, Wait, guys, let me check. Why suddenly I like very blank? What the heck? What did I do last time? It's this one. Of course. Oh wow, okay. I can't believe I can sorry. Some difficulties. Okay, full screen. Okay, let's see the answers. Yeah. So Ang Shujian is correct. Thank you, everyone. Thank you, everyone. Okay. Wow. Suddenly, we know YN, right? So we can find E1, right? Okay. Firstly, like this. So we know that E1, because it's a hum, right? So E1 equals E2 plus delta Z. So delta Z is just E1 minus E2. We know E1 is from the normal depth, right? So we find it first. So E1 is Y normal plus Q squared divided by 2G Y normal squared minus the critical energy. So E2 is actually EC, right? So you can, okay, so typically, right, if you want to relate energy and depth, you must use this whole equation. But there's an exception for critical depth. You can just use 3 over 2 YC. Okay, so in this case, right, the normal depth is how much? 0.914, right? 0.914 plus Q is 2 to 9.81, 0.914 squared minus 3 over 2. What's YC? 0.742. Okay, so yeah, so what we have, plug in your calculators. 0.914 plus 4 divided, wait, Q is 2, right? Yeah, Q is 2. 2 times 9.81 times 0.914 squared minus 3 over 2, 0.742. So you get 0.045 meters. So yeah, this one clear? Wait a second. Did I calculate wrongly? It's basically 1.1580 minus 3 over 2 times 0.742. 1.113. It is 0.045. Um, I forgot something. Sorry. I forgot something. You cannot just simply use this. Wait a second. How do you make new page? Okay, guys, it's not, I cannot do this question. It's just, I don't know what happened there. Like suddenly my mind blank. Oh gosh. Okay, I haven't covered this yet, but this is why drawing water surface profiles are important. Um, wait a second. Q squared over. Okay, I guess I'll just show you my solution. I don't know what happened to me today. Yeah, why is it like very different? It's 0.09191. I mean, we did use a different. I mean, we use assumption, right? So, um, okay, I guess I'll just be confident. Yeah, you guys get the same answer, right? As in, like, this is just yn plus q squared over 2gyn squared minus 3 over 2 yc. Okay, so you find, okay, I'll just write like 0.045 meters. Okay, let's continue. Okay, I guess our answer is quite far from the PYP solution because we used this assumption of the white channel. I didn't expect it to be this far in answer, lah, but I guess that it is what it is. So yeah, so this is our answer. Okay, let's continue. So number 3, suppose a bridge is to be built over the channel supported by a 1.5 meters wide square bridge pier. Calculate the flow depth at the bridge section and the flow depth immediately upstream. Okay, so what does this mean? I think Yukai asked about, I don't know, is it Yukai? I think someone else asked about the contraction, right? So this is example, like one example of the contraction. So we started with Q equals 16, right? Yeah, Q equals 16. So it's, so you can imagine, so this is top view. So you can imagine the channel to be changed. It has a change in width, right? So this 8, this is like, so 1.5, right? So this is 8 minus 1.5, which is 6.5 meters in width. So in this case, in this case, right, we have a contraction. So calculate the flow depth at the bridge section. So in this case, right, we have Q1, which is equals to 2 meters per second, 2 meters squared per second. Our Q2, right, is 16 divided by the new width, which is 16 divided by 6.5. So that's 2.46. So let's draw the energy diagram. This is Y, this is E. So in this case, right, we have this thing, but since it's contraction, we have this. Okay, so first thing first, you must check, is there choking? Okay, for energy equations, always check if there's choking or not. So in this case, right, so to find choking, we need to find the critical energy of the new curve. Because if the critical energy is above E1, then there's choking. If the critical energy is below, then there's no choking. Okay. So this is E2C. This is Q2. This is Q1. So let's calculate. So the critical depth of the second one is Q2 divided by G, or the squared. Okay, 1 over 3. So 2.46 squared divided by 9.81 to the power of 1/3. So let's calculate the 2.46 squared, 9.81 to the power of 1/3. So it's 0.8050 meters. Let's calculate the critical energy. So 3 over 2 IC, right? So it's 1.276 meters. So now let's check E1 with our EC2. So E1, right? It's this one. Whoops, I didn't calculate. E1 is yn1 plus 2 squared divided by 2 gyn1 squared. Yn1 is 0. What? 0.914, right? 0.914. So yn1 equals 0.914 meters. So let's calculate 0.914 plus 4 divided by 2 times 9.81 times 0.914 squared. So it's 1.158. Yeah, 1.158 meters. So if you notice, right, if you compare this to this, our critical energy is above our initial energy. So in this case, right, our diagram should be like this. So if our diagram is like this, then there's choking. Okay. If there's choking, so since E critical 2 is above E1, choking. Okay. So if there's choking, then as what I said before, what happens? Our energy moves. So this is our initial energy, right? This is E1. So our new energy is going to be E1 star, which is equals to E2C. So it will move along the new new graph. Yeah. So this is Y, this is E. So let's just calculate. So E1 prime is just E2C, right? Which is 1.276. Yeah, so this is the new energy, but then we are interested in, okay, the flow depth and the bridge section and the immediately upstream. So as in, like, we need to find the depth here. This upstream, this is the bridge section. So for the bridge section, it's actually, okay, because there's choking, that means that the Y, the new Y, is just the same as the Y critical, which is 0.850, because there's choking. So this is our new depth. This is our new depth. So this is Y1 star, which is equals to Y2C. So how about our initial depth? Well, our initial depth, right? Why did I draw E1 at here? So this is E1, right? Our initial depth will follow this new energy. So our initial depth, right, will be this point. Okay, so it will be this point. This is, this is Y2. Sorry, this is Y2, which is YC2. This is Y1. This is Y1 star. Y1 star is the new one. Okay. So sorry, this is E2 equals EC2. This is not Y1, sorry, 1.276 meters. Yeah, sorry. Sorry if I'm confusing you. Okay, sorry. So this is the new depth at the bridge section, Y2. Okay, this is the new depth above the bridge section, upstream. Okay, it's the Y1 star. So because the energy moves, right? So our depth will also move for the new one. So our new depth, you calculate it from this equation. So E1 star equals Y1 star plus Q squared, Q1 squared to be exact, divided by 2G Y1 star squared. Okay, so just plug in. So this 1.276 equals Y1 star plus Q1 was 2. Why do we use why do we use Q1? Because we are interested in our point upstream. Okay, our initial point that has been changed. Okay, so 2, 9.81 squared. Okay. So you multiply everything by y1 squared. So it becomes a cubic equation. So 1.276 y1 star squared plus y1 star cubed plus what's 4 divided by 2 times 9.81? It's 0.2039. So we have this equation, which is y1 star cubed minus 1.276 y1 star squared plus 0.20390. So for this one, right, just use your calculator, the cubic, like solving cubic equations. So I'll just input everything. So 1, negative 1.276, 0, 0.2039. So you will have 3 answers. So y1 star is negative 0.35, 1.11, 0.52 meters. So which one do you use? Well, first things first, you won't use this one because negative, so it doesn't matter. So how about these two answers? So these two answers is the alternate depth, the one that I told you before. For 1E, there are 2 answers. So according to the flow accessibility rule, if you start with subcritical, you must end with subs end with sub, super end with super. So let's check our initial point, which is E1, 1.158, right? And wait, sorry. So compare the normal depth, sorry. You know 0.914, right? You know that 0.914 is above 0.742. So our initial flow is subcritical. So our ending flow in our answer should also be subcritical. So in this case, we choose this one. Sorry, this one, 1.11, the one which is sub. So this is sub, this is super. So we choose this one. So y1 star is equals to 1.11 meters. So that's your answer. So we have 2 answers, which is this one. This one is at the bridge section. So this at bridge. This one is immediately upstream. So I think it's just it. Sketch and indicate the values obtained in parting on a specific energy diagram. You just use this actually. So I'll just make this neater. So there's choking, right? So we have this. Then we have the new Q, which is this one. This is Q2. This is Q1. This is our initial energy. This is our new energy. Okay. So our initial energy, right? This is E1. This is E2 critical. This is E1 prime, E1 star. This is Y1 star, Y1, and this is Y2. Okay. So is this clear? I hope this is clear. Sorry for the hiccup. As in, like, I don't know what happened. Like, but anyways, I hope you guys get what I'm trying to say here. Okay. Yes, I will send this file after this. I think I'll like for this question. I think what's it? I'll change my. I'll review my workings. I don't know what happened there. It's like I don't know. Suddenly cannot think. Okay. Um. Well, it's already one, so I think we can skip first because this is actually the same question. This is just like for your practice, but I will do this question and send it. Yeah. Should push back further, as in. Yeah. Okay, I will review my workings. Okay. Wait, no, it's correct. I think our initial depth is 0.914. Our initial depth is 0.9. Our new depth is 1.11. So it should be correct. Yeah. Pushed up as in, what is pushed up? Yeah, this is pushed up. This is pushed up. As in like, yeah, this is our y1, right? Y1 star is the new depth. Um, um, yes, I mean this is our depth, right? Okay, so the story is like this. So y1, right? You want to, and then you want to check if, so because there's contraction, q will go that way. So q increases. Okay, and then you want to check if the q increase is beyond this line or not. So we start with this black curve, right? And then we have E1 here. We have E1 here. So we want to check, does this black curve goes to the right beyond the E1 or not? Apparently it is. So there's choking. Yeah. So this E1 will go to this point, which is like on the critical energy of the second curve. Yeah. So this is our ending point, Y2. But then our starting point will increase to Y1 star. So that's what's happening. Yeah. So yeah. Okay. So yeah, I hope that's clear. Again, this one I'll skip. I didn't expect myself to take that long, honestly. I don't know. That hiccup. Okay. Anyways, I think this is what all of you have been waiting for, the qualitative GVF, the one drawing, because I think most of you are some like confused. Okay. So there are 9 steps. Okay, 9 steps in total. I will explain each step one by one because it's pointless if you go directly to the drawing if you don't understand. So let's start with the first step. So if you want to plot the water surface profile, you need to determine the type of bed slope. Okay, is it mild, steep, critical, horizontal, or adverse? Okay, so actually the first step and the second step is together. You need to find yn from Manning's. You find yc from yc equals q squared over g 1/3. Okay, so how do you, so yeah, this is how you determine the type of slope. So mild, right? For mild, yn is bigger than yc. I'll make a new page, I guess. So I'll go to point number 1. Point number 1 and 2, actually. Point number 1 and 2. Yn from Manning's. Yc from yc equals q squared divided by g 1/3. Okay. So for m, yn is bigger than yc. For s, yc, so yn is less than yc. Critical yn equals yc. Yeah, this is the important ones. For the horizontal and, okay, I mean, why not lah? Y horizontal, yn is infinite. Adverse also, actually. Why is it infinite? Because okay, let's go to the third point first. I'll explain why is it infinite later. Okay, so first and second point is that, so you grab the critical and normal depth from Manning's and the critical flow. The third one, given a long fetch, flow will always try to revert to normal flow. So if you link back to uniform flow, basically what it's saying, right? If there's no obstruction, the flow is always normal. If there's no obstruction, flow is always normal. So in this case, right? Let's say you have this is mild, let's say. This is y critical. This is y normal. So if there is no obstruction, so you see, right, there's nothing, then the flow will always be normal. Okay. For steep is the same, but for steep, right? This is steep. The critical will be above the normal. That's the only difference. But if there's no obstruction, it will always flow at the normal depth. Okay, it will always flow at normal depth. But then you might ask, what happens with, I mean, critical, yeah, you have normal. How about adverse and adverse and horizontal, right? For adverse and horizontal, there's no normal depth. It means there's always GVF, always GVF. There's no normal. So for mild, steep, and critical, if there's no what's it called? If there's no obstruction, the flow is always at normal. But since our slope, like horizontal and adverse slope, right? It doesn't have a normal depth. The flow is always GVF over the horizontal slope. Just remember that. Okay? It's always GVF. It's not normal flow. But for the rest, if there's no obstruction, normal flow. So I hope that's clear for number 3. For number 4, you need to select the appropriate curves. I won't go through this. I mean, this will be clear when there's obstructions, but I want to explain this one first. So we have one letter and one number. The letter indicates the type of slope. So if steep, it's S. Mild is critical is C, mild is M, and so on. The 1, 2, 3 indicates the position where the GVF forms. Okay, the position where the GVF forms. So we divide it into 3, top, middle, and bottom. Top is 1, middle is 2, bottom is 3. So for steep, right, the GVF that forms on top is S1. The second one is middle. The last one is bottom. What do I mean by top, middle, and bottom? It is divided by the critical and normal depths. Okay. So if you see, right, for steep, right, 1, 2, 3. Mild, 1, 2, 3. For critical, because the YN and YC is critical, as in like together, I mean. So I mean, you can logic, right? This is top, bottom. This is the middle, right? But then if YC and YN is the same, there's no C2. I mean, there's no space for C2. Okay. Yeah. So the numbers indicate the position of the GVF. Is it top, middle, or bottom? For horizontal, there's no normal. Normal is infinite. It's like infinitely high. So there's only H2 and H3. Adverse also 2 and 3. Okay. So I hope this is clear. I will tell you the symbols first. This one later. Okay. Next, curve should not allow. What's H without any subscript? Oh, this one. This is from the slides that I sent you in the group. This is why. No, this is flow depth. This flow depth. This is actually why. Yeah. So it's flow depth. If the flow depth is above critical depth, then it's A2. Basically, it's saying that. Yeah. So this is like the position of the water depth. If the position of the water depth is both above critical and normal for steep, then it's S1. If the water depth is between this and this, basically it's just saying the location of the GVF. Yeah. So again, top, middle, and bottom. So rule number 5, curves should not be allowed to extend beyond their own category. That means that M curves only happen in M slopes. So what do I mean by this? Let's say you have M, and let's say what you want, S, I guess. Yeah, M and S. What do I mean by this? So let's say you have M3, right? Let's say you have M3. M3 cannot go beyond. So you cannot have like this is M3. Cannot. Okay. It's a very simple thing, but I don't know if some people might get some mistakes. Okay. So M slopes must only happen in M curves must only happen in M slopes. S curves only happen in S slopes. Oh my gosh. Yeah, English. Okay. So it cannot go beyond their own region. Okay. M is in M, S is in S. Okay. It's a simple thing, but I don't know if people might forget. Okay. This is not S1, by the way. This is S3, I think. This is M2. Whoops. Okay. Okay, but that's later. Okay, so number 5. Again, M curves only happen in M slopes. S curves only happen in S loops. Number 6. So this is something that people might confuse of. I know that Tan Sun Kiat mentions this a lot, Mr. Tan Sun Kiat, but I will explain this now. So for supercritical flow, the control is upstream. For subcritical, it's downstream. What does this mean, right? supercritical flow only cares with upstream obstructions. For downstream control, that means that it only cares with downstream obstructions. Okay, so I think the best example to see, right? Best example to see this is the mild to milder, steep to steeper. I think that's the best example. So let's say this is mild, this is milder, mild to milder. Okay, so let's compare the two. So this is steep to steeper, steep to steeper. So what does this mean, right? In mild, you know the flow is subcritical. Subcritical flow have downstream control. So let's check the first region, okay? Let's check the first region. So the first region, so imagine you have like a box. So you ignore the right and left. You ignore the right and left. Okay? Subcritical has downstream control. So for this region, as in like this region, you check downstream of this region. Are there any changes in bed slope? Are there any obstructions? The answer is yes, because there's a change in slope, right? So downstream of this section, downstream of this section, there's a change in slope. So there's an obstruction. If that's the case, then there's GVF. Okay, there's GVF in this. So what's the GVF? The GVF will be, okay, I'll explain this later, but this is M2. Okay, basically it's saying if there's a downstream obstruction, there's a GVF. So now let's check the second portion. This is the milder slope. So again, cover the right and left. I think it's easier to cover right and left. Remember, mild means you have subcritical flow. That means downstream control. So you only care about the one downstream. Are there any obstructions here? So this is the portion we are interested, right? So the downstream of this portion is this portion. Are there anything here? The answer is no. If there's no obstruction, the flow is always normal. So it's back to point one. Back to point three. If there's no obstruction, flow is normal. So since this portion, downstream, there's no obstruction, so the flow is normal all the way. So that's clear. So now let's go to steep slope. So steep slope has supercritical flow. That means there's upstream control. Okay. So let's check the first portion. So again, cover your right and left. I think it's easier to do it this way again. So for this portion, this is upstream, right? So are there any obstructions upstream? The answer is no. So the flow will be normal all the way. Normal all the way. Okay, now let's check the second section. So cover your right and left. I mean, usually I do this with my hand, but in this case, I cannot put my hand. So I'll just cover it with my pen. So again, for this steeper slope, are there any obstructions on top? The answer is yes, which is the change in slope. So if there's obstruction, then there's a GVF. So in this case, the GVF will be S2. Is it S2? I don't know. It's S2, GG. Yeah, S2. Yeah. Okay, I will tell you how it's M2 or S2 later, but the point is, okay, wait, should I explain now? Okay, I should explain now. Okay. Okay, but you get the point, right? The point that I'm trying to say, right? The upstream and downstream control, right? Downstream control means it only cares about what's happening downstream. Upstream control means, oh yeah, mild to milder is M1. Thanks. Um, let's go back to first principles. We need to, okay, this is the YN. YC, sorry, this is YC. YC is constant, by the way. No matter what the slope, what the slope is, YC is constant. Because again, if you go back to the specific energy diagram, right? 1Q, 1YC, no matter what the slope is. Okay? 1Q, 1YC, no matter what the slope. Okay, so for mild, right, we have YN here. If the slope is milder, logically, logically speaking, our flow will be slower. So our flow depth will be higher. So our normal is above. So for steep, right? Steep, we have this one, y normal, and steeper means our y normal is below, even lower. Okay, again, let's check this one. Cover your right and left. You check downstream. There's a change. So okay. Now I'm going to tell you how to plot the curves. So okay, sorry. So let's start with this one, mild to milder. You will, so where do you start? Because again, there's no obstruction. So for this one, right, there's obstruction at the right. Okay, there's obstruction on the right. So you need to go. So there's GVF here. There's GVF. For this portion, if you check downstream, there's no obstruction. So it's normal all the way. Okay. So how do you know the type of slope? You check where you come from and where are you going. In this case, right, our mild slope, we are going from normal depth. Where are we going? We are going to somewhere above the normal depth. So if you check the table, so let's check the mild. So you need something to go from the normal depth to a point above the normal depth. So you check which one is appropriate. So you start at normal, you end at somewhere above the normal depth. So M1. Okay. So this is M1. Okay, so let's go back to steep and steeper. So again, you check this portion. Supercritical is upstream control. So are there anything? The answer is no. So the flow will be normal all the way. Then you check the steeper section. You check the upstream of this section. So you cover right and left, I guess. You check the upstream, right? Are there any changes? The answer is yes, which is the change in flow depth. So there will be GVF. How do you know which GVF it is? Again, you end at normal. You start at somewhere above the normal, right? Somewhere above the normal and between the YC. Am I correct? Like, don't look at this portion. So you start from this portion, you end at Y normal, right? So again, check the graph. Sorry, check the table. You start from somewhere between YC and Y normal. You end at Y normal. So the curve is S2. In that case, draw S2. So this is S2. Okay, sorry for all the hiccups today. But you get what I'm saying, right? You get what I'm saying, right? So downstream control means you only care about the one downstream. Upstream controls means you only care about the one upstream. Which curve you need to use, you see the table. Where do you start from and where do you end? Okay, I hope this is clear. Any questions so far? Okay, I think we can go back to number 4 for a bit. Okay, let's go back to number 4. So I'll do the same thing here. So for mild, right, Y normal is this one. For steep, Y normal is this one. Okay, so let's check the first portion. So let's cover right and left. So mild slope, right? It has downstream control. So we only care on what's happening downstream of the portion. So on this portion, downstream is this one, right? Are there any changes? The answer is yes, because there's a change in slope. Okay. So we need to go to, because we are going down, right? We need to go to the critical depth. Okay. We need to go to the critical depth. In this case, right? Okay, sorry. You start from the normal depth, you end at critical depth. So let's see which part we can use. So this is mild. We start from normal depth, we end at critical depth. So it's M2. Okay. So let's go back. So let's draw. This is M2. Now let's check the steep portion. So cover right and left. Cover right and left. So for steep, right, it's upstream control. So you check the one upstream. Are there any changes? The answer is yes, because there's a change in, what's that called? there's a change in channel slope. So we want to go from critical to the normal, because we know the ending is always at normal, right? The ending is always at normal. But then we have from critical, right? So let's check the table. So we start from critical and at normal. So we have S2. Okay, so let's go back. So this is S2. So done. Yes, so for this case, mild to steep, when drawing mild portion will reduce to YC. That's my next point actually. So, so, um, so transition between sub and supercritical flows. This is quite important. There are only two possible cases. The first one is sub to super. That case will have choking. So the one that we have now is, we have, what's that called? We have steep, no, mild to steeper, right? Because it's mild is sub, steep is super. So there will be choking. So it will always pass YC. It will always pass YC. So this is what I mean by sub to super. The second possible one is you are converting from supercritical to subcritical. The only way it can happen is through hydraulic jump. We haven't this. I will cover this later, but just keep in mind, sub to super is choking. The one that we've discussed in the energy. Choking means YC. Super to sub is always hydraulic jump. Okay. So next, I will show you number 7 with number 8. So for number 8, right? Oh, 8 and 9 is okay. 7, 8, 9 is together. So number 8, if there's a gate or dam, elevation must always be above critical and normal. So it always at the very top. Okay, because you can think of it as, if you have a gate, right, the water will stack here, stack at the gate. That's why the depth is always very deep. Okay. And okay, I will show later. It's fine. Like don't worry. 7, 8, 9 comes together. Last one is hydraulic jump. So for hydraulic jump, for M, H, and A, mild, horizontal, and adverse, the GVF forms before the hydraulic jump. For S slope, it always happens after the hydraulic jump. Okay, so 7, 8, 9 together. Let's do it. 7, 8, 9. So add page. Okay, so what's 7 and 7, 8, and 9. Okay, so I think it's a best example is to, okay, this is mild. Okay, so this is a sluice gate. This is mild slope. Mild slope. Yeah, mild slope. This critical. This is okay. The normal is too high. I'll make it this much, just to make it easier. Okay, so so mild, right? Again, downstream control. But before we go to downstream control, right, I want to state something. Should I go control? Okay, never mind, guys. We need to go to control points first. Oh, okay. So okay, sorry for I really don't know like the arrangement that I need to teach you guys, but 7, 8, 9 and control points are together. So let's go to control points first. Okay. So control points, right? I think by definition, it means that there's a definite relationship between discharge inflow and flow depth. Okay, and these are examples of control points. Okay, but I think in a more monkey language, right? It's basically saying no matter what slope, must go to that point. Okay, I will explain what. Okay. Basically, like control points, right? It's basically a point that you must go no matter what type of slope it is. Okay, okay, but then what, when you answer the exam, right? Of course, you use there's definitely relationship between discharge and flow depth. But just for your understanding, no matter what slope, you must go to that point. That's what a control point is. Okay. So example of control points, right, are gates, weirs, and sudden fault in channel. Yeah. And critical flow sections, like critical flow points. So what's it called? Like control points may not be critical flow sections, but critical flow sections are always control points. Okay, I think let's go to this sentence first. Let's go to this sentence first. Like no matter what slope, you must go to that point. Okay, let's start with this image. So no matter what slope, right? If there's an obstruction like a gate or something, you must always go to this point. And this point is, as I described before, it's point number 8. So before any gate or dam, the elevation of water is always above critical and normal, and it's a control point. So no matter what slope, right? So steep with gate or mild with gate, right? You must always go on top. Okay, it must always go on top. So that's what a control point is. So yeah, so if you see, right, this one, right? So this is mild, this is steep, but no matter what type of slope, right? If you have a gate, you must always go on top. You must always go like in a very high point. And then this point, right? You must always go to the opening. So you get what the control point means, right? So if you have a structure, um, the structure will control the flow. Like no matter what type of slope, right? No matter you put this sluice gate in a mild slope or a steep slope, you have always, like, your flow must always go through these 2 points. So that's what a control point means. Okay. So I'll connect I'll connect to this. So for this one, right? So this is a sluice gate. There are control points. There are points that you need to go, no matter what type of slope. For sluice gates, it's always a point above the normal and the critical, and always like at the opening. So no matter what, you must go through this point. So, and then let's combine what we've learned before. So we have two sections, this section and this section. Let's focus on the first section. So cover left and cover right. It's a mild section. So there's a downstream control. So you check the one downstream. So is there an obstruction? The answer is obviously yes. Okay, so there will be GVF. So where does the GVF go? We start at Y normal. We end at somewhere above normal. So this is, if you check the table, this is M1. M1. Okay. So that's the first thing. Second thing is, for mild, right? For this section, you must always start at, okay, actually like this. Mild, let's cover to the left and cover to the right. Do you need to go anywhere? As in like downstream control, right? You check, are there any obstructions? The answer is there are no obstructions downstream. So the flow will be normal all the way. But then if you see, right, there's one problem. There's one problem. You start at subcritical flow. You end at supercritical flow. So in this case, right, you have super to sub. So in this case, right, if you check point number 8 or number 9, I forgot which did I put. If you have super to subcritical flow, there's hydraulic jump. So there will be hydraulic jump here. Okay, there will be hydraulic jump. Okay, and then again, if there's a hydraulic jump, for mild slope, mild horizontal and adverse, there's always a GVF before the hydraulic jump. So this is M3. Okay, so this is what I'm saying. So our GVF always happens before the hydraulic jump for mild slope. So any questions so far? I hope this is clear. I hope this is clear. Okay, so this is a control point. So again, you check downstream. You need to go to this point, right? So you need this GVF, and then because you need to go from super to sub, you must have a hydraulic jump. And because the hydraulic jump happens at mild, there's M3. Is this clear? I hope this is clear. So let's go to the steep case. So let's say this is steep. Please, let's say this is steep. So um, y normal, um, y critical. Okay, so let's say you have a sluice gate. First thing first, you need to know the control points. Okay, digesting. Okay, so control points, right? No matter what the slope is, you must go there. Okay, in this case, right, for sluice gates, it's always above the normal and critical, no matter what. That's a control point. Whoops, yeah, this is YC, this is YN. Okay, okay. So for sluice gate, right, the control point is above and below. Okay, so no matter what type of slope, sluice gates need your water to go up and down. Okay, as in like up here and down here, no matter what type of slopes. Okay, okay. So let's start from steep. I guess we'll start from this portion. I think it's easier. So you covered this one. Okay. So for steep, right, it's upstream control. So upstream control. Are there any obstructions here? Upstream of this section. Are there any obstruction? The answer is yes. So there's a GVF. So again, you need to end at y normal, but then you start at somewhere below y normal. So if you check the table, this is S3. S3. Okay, actually, because the table is like something like this. Yeah, this is Y, YC, YN. This is for steep. Okay, so you start from below normal, you need to go to normal. So this is S3. Okay, this is S2, S1. Okay, so that's our bottom portion done. Okay, now let's for this one. Remember that we must go to this point. Okay, because due to the control point. Okay, because the sluice gate forces it to go there. So in this case, right? Um, how should I go? Okay, before that, let's check this portion. So cover right and left. Steep is upstream control. Are there anything upstream? The answer is no, right? So the flow will be normal all the way. Normal all the way. But then this is the case. Due to the sluice gate, you must go up, no matter what. Okay, so there's a mismatch, right? So our upstream control says that you can go normal all the way, but then the sluice gate says no matter what, you must go to this point. So there's a mismatch, right? So in this case, right, there's a hydraulic jump. So there's a hydraulic jump. But then, based on my point before, for steep, right, hydraulic jump comes first, then S1. Okay, so this is your water profile. So is this clear? I hope this is clear. Like once you're clear with these cases, you're done. So I'll review. So first thing first, you need to draw the type of bed slope and plot the critical and normal depths. Okay, and then you need to know that if there are no obstructions, the flow is always normal. Okay, and then this one, there's three types: top, middle, bottom. So 1, 2, 3, and the type of slope which is SMHA, SCMHA. Okay, and then next, curves must stay at their own sections. And then we have for supercritical flow, they only care with upstream obstructions. For subcritical, they only care with downstream obstructions. And then before any gate or dam, there's always a control point which is above. So always type 1. Okay. Lastly, for hydraulic jumps, yeah, M3, HTA3, or S1. So either one. Okay. So yeah. Yeah, and then control points are the points that no matter what, you must go to that point. Okay, no matter what slope. So yeah. So I mean, okay. So why is a critical point control section? Because like if you go from sub to super, right? Actually, this is a reference to the EY diagram. You remember the principle of superposition, right? Let's say you start with sub, you cannot go to super. So for you to go to super, right? Actually, what you need to do, right? You need to go to the critical point, then you go to the super. So that's why it's a control point. Like no matter what, you must pass through this YC. No matter so if you start from sub to super, you must pass to YC. Okay, that's why it's a control point because you know that it will definitely pass YC. So that's the reason why YC is a control point. So okay, I guess we can do questions. So okay, I'll give you some example first. So this one, right? We have an obstruction. So again, this is mild slope. So for this one, right, check this one. Uh, um, so this portion, right? Are there any obstruction downstream? The answer is yes. There's a weir, right? That's why there's M1 here. So normal M1, okay. And then again, this is a control point. No matter what, okay. This is sub to super, right? Sub to super, right? The transition is choking. That's why we have YC here. So from M1, you go to YC, you go here. Okay, and then you have, and then remember that this section, right? It must be normal because there's no obstruction. There's a mismatch. That's why there's a hydraulic jump. And then M3. Still processing. I hope this is clear. Where is there a control point at the end? You mean before the hydraulic jump, is it? Ah, because I haven't covered this yet. I will cover this in the next chapter. But because this is called the conjugate depth. So for the hydraulic jump to happen, like there's a specific depth that you must go before jumping. It's called the conjugate depth. That's why it's a control point. I will explain this in when we get to momentum. Okay. Yeah. Then for sluice gates, yeah. So as I said before, there's M1 because again there's obstruction, right? So there's GVF M1, and then from this point, there's no obstruction here. That's why it's normal depth. But then there's a mismatch. So there must be a hydraulic jump. Yeah, and then this is the same as I described before. Lah. So you must go here. So this is start with normal. There's a mismatch here. So hydraulic jump S1. Then you start below. It must go to normal. So S3. Okay. Then from reservoir. This reservoir is a bit special in a sense, I guess. So what do I mean by this? So let's use our principles. This is mild, right? This is mild. So this is our portion. So let's cover right and left. So mild, right? For mild, we have downstream control. So we check downstream. Are there any obstructions? The answer is no. So we can go normal all the way. That's why this is like normal all the way, and there's like only a slight dip. Okay. So yeah, and then that's why like the entrance depth is why normal. But then for steep slope, right? Let's say for steep slope. So there is an upstream control. So let's check this portion. So cover right and left. So you check upstream. Do you have a change? The answer is yes, there's a change. Right? In that case, there's a GVF. So for the GVF, right? We start from a point in the middle, then we go down to the normal. Because reservoirs typically are higher than, yeah, like typically reservoirs are high. That's why we have S2, which goes from Y critical to normal depth. So you see the difference, right? For mild slope, the entrance is Y normal because there are no obstruction downstream, so it can go normal all the way. For steep slope, there's an obstruction upstream because again, upstream control, right? That's why it must pass through Y critical. This is y normal. So yeah, I hope you can use the principles that I taught you. Okay. So let's go to the, yeah, this is, so okay, so this is like from the reservoir. So this is like input, right? It's going into the river. So let's go to the, like, going out of the river. So let's say you have a reservoir, right? So for mild, like, we have downstream control. So are there any obstructions? The answer is yes. So there's a GVF. In this case, the GVF is mild 1, M1. The same goes to this one, the free overfall for mild slope. So again, downstream control, right? Downstream control, there's a change. So there must be a GVF. Okay. For free overfall, we assume that this is supercritical. Because I mean, free overfall, right? It's very fast. So that's why it's M2, because it goes to the critical depth. Okay. So for steep slope, right? Again, it's upstream control. So for this section, we only care about the one upstream. There's nothing. That's why it's just normal all the way. Normal all the way and then just go down. Okay. So again, let's do some practice. Well, I know this is taking a long time, but okay. So actually, right, water profile sketching will not come out by itself. It will only but it will always, like, again, in a combo question with other principles. It also comes with, what's it? But it also helps you to solve questions because you can visualize the profiles. Yeah. So I guess let's do this. So for this one, right, let's just do this very quickly because this is just applying that what we've taught before. So steep. Okay. By the way, this is critical depth. By the way, yeah. So let's do it steep. So steep, right? Normal depth is here. We have an obstruction. So this is a control point. So no matter what, you must go to here. Then steep, we have upstream control, right? We have upstream control. So you can go normal all the way. Wait, but then there's a mismatch. If there's a mismatch, then there's a hydraulic jump. So there's a hydraulic jump. So how does the hydraulic jump form? It's always this one, and then S1. Okay. And then we have horizontal. Remember, this is a control point. This is also a control point. So you start here. So this is given. So we need to go up, right? We need to go up. So there's H3, and hydraulic jump. Okay. Okay. And then horizontal, right? Because there's no normal flow. Remember, like, horizontal doesn't have normal. Normal is absent. So it's H2. Okay. This is H2. And then you have this one, mild. Why is this is normal? Why are there nothing? Well, we only care about the one downstream. Actually, downstream there's something. Oops. So in this case, we go from normal because downstream, right? Again, mild is downstream control. We check there's a free overfall here, right? So it must go. It must have a GVF. So this is the GVF. It goes this way. So what's the GVF? If you check the table, this is M2 because for normal, right, I think, sorry, for mild slope, this is M1, M2, M3. So M2, right, goes from normal depth to the critical depth. So this is M2. Okay. So this is quite critical. So this is also a control point. So yeah. So any questions so far? I hope this is clear. This is just combining the ones that we've learned. Yeah. So let's go to the next question. So again, steep. I mean, at this point, you know the pattern. This one must have a control point. So this one must go like this. S1. Okay. I hope you can see the pattern now. So steep, right? This is S3. Because again, this is y normal, right? This is y normal. You start from below, and then if you see the table, right, this is y normal, sorry, y critical, y normal, bed slope. For steep, right, it's like this. Yeah. Oh yeah, you need to know the profiles by heart. So you need to memorize the table. But I think like at this point, right, you need to like once you do this, right, I think you'll get used to this. So you start somewhere below normal, you end at normal, right? So this is S3. So yeah, so this is S3. Okay. So S3 to the normal depth. And then there's steeper, right? Steeper. Steeper again, we just checked the one upstream, right? So this is S2. Okay. Um, S2. Okay, something that I forgot to discuss just now. If there's a steep slope and there's a mild slope, again, this is super to sub, right? Super to sub. If you check the one that I wrote, super to sub have hydraulic jump. Okay. So some cases is this one by the sluice gate. There's one more case which is steep from steep to mild. Steep to mild. Because one is super, one is sub, right? Okay. Okay, so there are two choices that you can go. First thing first, right? The hydraulic jump happens at the steep slope, S1, and you go to the normal depth. The second choice is you have M3, hydraulic jump at the mild slope to the normal directly. Yeah, this is one case that I forgot to mention. Okay, so there are two choices. Which one do we use? It's dependent on conjugate depth. So again, this one is next chapter, so I will explain this later. But for now, just remember that if you go from steep to mild, right, you have S1, you have M3. So as in like it depends. If it happens at the steep slope, hydraulic jump, then S1. If it happens at the mild slope, M3, then hydraulic jump. Okay. So let's go back to the question. So for this one, right, we have two choices again. So we have M3, then hydraulic jump, or we have hydraulic jump, then S1. So so we have two possibilities. How do we know? We know by using conjugate depth, but we haven't learned that yet. So I'll skip that first. We have this one. So there's M1. Then yeah, this one just I don't know what's this one. I mean, as in like this is just continue lah. So is this one clear? I hope this one is clear. Okay. So again, so at this point you should be able to plot these. So I'll just give you the answer. You guys can think later. This M1, M3, with M3, this one, and then there's, oh wow, it's a bad drawing. Okay, this is M3, then there's hydraulic jump, and then mild to steep, sub to super, right? There's a choking. So there's choking right here. So this is YC. So this is M2, this is S2. Okay. And then we have steep to critical, right? Steep is upstream control. So yeah, we don't care. Critical is, I think it's upstream, if I'm not wrong. So again, we care what's happening upstream. So it's going to be C1. And then this one, right? For critical, okay, actually critical is a very rare case, but critical cannot have cannot have hydraulic jumps. Yeah, it's a very rare case. It's a very rare case. So this is C3. Because critical slope cannot have a hydraulic jump, but it's a very rare case. So you don't need to care yeah. So this one is just C1. Yeah. So this is your profile. Okay. So let's go to the next one. So we have malt, we have a reservoir. Again, malt is downstream control. We only care what's happening downstream. So this is just directly Y normal. So this is Y normal. So no GVF, no GVF. Because malt, we only care about what's happening downstream. Yeah, wait. Okay. Then for malt to steep, right, we have, again, malt, we care what's happening downstream. There's something. So there's a M2. Then for steep, we care on what's happening upstream. So upstream, we have something, right? So there's a GVF. In this case, it's S2. Okay. And then for adverse, right, there's a given level. So this one, right, you need to have a hydraulic jump. And this is S1. Or you have a hydraulic jump here. This is A3. You have given. Okay. It's a very tight spot too. Okay. So you have S1 or A3. And then because adverse, right, adverse doesn't have a normal slope. So there's always a GVF. There's always GVF. So in this case, right, this is A2. Okay. And then steep slope, right? You need to go from sub to super. So in this case, right, it will go like this. So this is A2. This is S2. Okay. Critical, very rare chance. Adverse, more likely, but less likely than mild and slope. Because the typical slopes, right, always mild and steep. Adverse is actually okay. So mild and steep is like the most common. Horizontal and adverse are quite rare. Critical almost never. Yeah, I mean, I think critical is the hardest, but critical usually you don't have because critical flow is very unstable. Yeah. So, anyways, let's okay. I mean, this one again the same thing. Okay. I mean, I've been doing this for I don't know how long. So this S1, then this one, and then we have oh wait, mild, right? So this one M3 first. We have a hydraulic jump, and we have normal. We have normal, right? And then mild to steep. Then we have M2 and then S2. So M2, S2, steep is always hydraulic jump, then S1. Then this one free overfall, right? So yeah. So yeah, I hope this is clear. I mean, this is like all the same questions here. So steep, right? For steep, okay, reservoir to steep. Then there's this thing, which is S. Okay, this is YC. This is S2. Yeah, this is S2. Okay, for steep, it's always hydraulic jump first. So hydraulic jump, then S1. Then this is mild, right? So mild means M3 first. Then hydraulic jump to normal. Then lake. Lake. Okay, for the lake, right? Again, you check the level of the lake. If the level of the lake is above the normal, M1. Because again, the M profile is up, up, like this. But in this case, right, because the lake is a bit below, we have M2. M2. This is control point, this is control point, control point, control point. Okay. So I hope this is clear. So I have done 9 questions. If you are still confused, you guys can check this diagram again. I will send the file anyways. Okay, but so far so clear, right? I hope because like this is very important. This is very important, really important. Yeah. Today I think I will be taking like 3 hours, around the hour. So the ones that can go longer can stay, but the ones that need to go 3 p.m. also fine. I will record. I mean, I'm recording this anyways. Yeah. So yeah, I'll scroll slowly so you guys can see first. Okay. Okay. Oh wait, shoot! I have like one more. What the heck? Okay, I guess this one, right? What the heck? Oh, okay. For this one, right? So don't okay. The point of this question, right? Don't worry about these shapes. This is a sharp crested wire, sharp crested weir. This is a spillway. This is similar to the broad crested weir, so you guys don't need to worry. So this one, right? So you start here. You have M1, then you have this one. So it is similar to the sluice kit, but it goes over. Instead of getting blocked, it goes over. So actually, this is YC actually. But anyways, this is with M3, hydraulic jump, normal, and then M2, S2. Then we have, okay, this is control point again, this control point. So with home, this is control point, right? This is control point. So you need a hydraulic jump. There's one. So like this, and then you have, oh, this is mount. So this is also going down. Also M3, hydraulic jump, normal. Okay. So yeah, someone asked me privately if after weir it must go back to the normal depth. Can you go from M3 to S3? The answer is no. You must go to normal first. Yeah. So you cannot like, okay, you cannot have like M3 S3. You cannot. Okay. It's always M3 first. M3 normal depth, then M2 S2. Because I mean the only time there's like two GVF back to back, right? It's only Malthus steep. Is this one. The was it the M2 S2? That's the only one that has back to back GVF. This one. You cannot have like, I don't know, M3 and S2. Cannot, okay? um we always assume that we always assume that the channel is long enough. Yeah, I mean this might seem very short, but in actuality it's very long. We always assume it's very long. Yeah. So for these two questions, I will leave it to you guys. Okay. I will send the one that I have answer on. Okay, shoot. I think I'm taking too much time. Okay, so control point, I think you know why. Just was it discharge and depth. Why is it important to identify control points? This is to measure Q, because if you know the depth, right, you can find the discharge. So to measure Q of the river, also can to 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 predict water surface profile. Okay, and then upstream and downstream control point. There's a lot of examples. So for, I mean, sluice gate, right? This is a downstream control point because you need to go to like this. See, you need to go to that point, right? This one is an upstream control point because you need to go from down here. So this one is a downstream control point. This is an upstream control point. Okay. So I hope this one is clear. So I mean, another example would be like the mild to mild to steep, mild to steep. See, you have like, I mean, you must pass through the YC, right? So you have M2 and S2. So this one, right? This for the one upstream is a downstream control point, and like for the steep slope, this is a upstream control point. Yeah. So there's actually a lot of examples. Okay. So um, shoot, I have like a bunch of questions. Um, okay, but I will show you like how to solve the question based on our sketch. So let's say this one, right? So you have a reservoir 3 meters above the channel bed at the entrance section. So number one, what happens when the slope is steep? So you need to find the unit discharge, right? Unit discharge when the slope is steep. So okay, I'll be quicker, I guess. So this is steep, this reservoir. So based on what we have learned, right? For a steep slope, it must pass through the YC. Okay. See, it must pass through YC. So you have, wait, okay. So in this case, right, if you are finding the unit discharge, because you know that the entrance to the steep slope is critical, well, it's just Q equals, wait, YC equals Q squared over G 1 over 3. So Q equals to square root of GY cube. Okay. So where do you get the Q from? You get the, wait. Oh, you don't even need this, I think. Okay, sorry. Let's do it step by step. So you're given the reservoir is 3 meters above the channel bed. This means specific energy equals 3. Okay. For reservoir, it's always like this. If it's 3 meters above the channel bed, then the specific energy is 3. Why is it 3? How to explain? So specific energy is y plus v squared over 2g, right? Right? For a reservoir, v is 0. So for a reservoir, the specific energy is just y. That's why E equals 3. Okay? Because v reservoir equals 0 and E equals y plus v squared over 2g. Okay? So in this case, right, if you want to find unit discharge, you can find the energy. So no, sorry. But then when you go from reservoir to steep slope, the condition is critical, right? So you know that the y critical is just simply 2 over 3 EC directly. You can directly go. So 2 over 3 times 3 equals 2 meters. So again, Q equals square root of GY cube, YC, sorry. So just square root of 9.81 to cube. So you find this. So that's part one. Let's go to part two. So for part two, right, what happens when the slope is mild? Then the uniform flow depth is this much, and sketch the water profile. So again, we have reservoir, we have mild slope. Again, based on what we have learned, right? Because mild slope only cares the one downstream, right? So you can go normal all the way. So in this case, if you have a reservoir, it will just drop to normal. So you know that the entrance is directly normal depth. So in this case, right, because this is normal depth and you have the Manning's equation, then you can find, is it rectangular? Wait, is it white? Oh yeah, it is wide. Wide rectangular channel. See, wide rectangular channel. So we can use Manning's Q equals 1 over N. La, 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 A. I think I'll use V. Yeah, I think I'll use V. So 1 over N RH to the third, which is SO half. So we have 1 over V equals 1 over 2.3. Oh, we have YN. Oh, sorry. It's YN. So this is okay. Do we have the channel slope? Don't have it. Wait a second. So you need to find the Q, right? Small Q. You know E, you know Y. Oh yeah, sorry. Okay, you can use this directly. Sorry. So E equals Y plus Q squared over 2GY squared. But since you know that the entrance to a mild slope is a Y normal, so you can just directly, this is YO. So 3 equals, what's YO? YO is 2.3. 2, so Q equals, you count. Okay. So basically you get the point, right? So sketching only helps you to solve questions. Usually it's not by itself. But I don't know lah. I mean, I don't know, like during the real finals, do they ask us to sketch like this, or do they ask us like numerical? I'm not really sure. Yeah, but sketching is important. Okay, so I think I spent a lot of time, but I hope like that much time, right? I hope you guys are really clear. Okay, so for hydraulic jump, right, it's not a lot. So again, I will cover about. So you remember, right? If there's a steep and mild, there's two possibilities, right? So now we are going to learn. Yeah, we are going to learn about this. So for a hydraulic jump to happen, so no, sorry, when a hydraulic jump is happening, energy is not conserved. Momentum is conserved. Okay, you just need to remember these two statements. Momentum is conserved, energy is not. Okay, so basically what it's saying, right? So the momentum at this point is the same as the momentum after the hydraulic jump. Sorry, right before and right after. Okay, so this is the momentum equation. You don't need to memorize this. Um, this one is more important, but I will explain. I mean, it's good to memorize this lah, but usually it's only proving questions. Okay, but for calculation wise, I think this one is more important. Okay, so again, because momentum is conserved, okay, before that, we have the momentum equation, right? If we plot it, it becomes something like this. It's similar to the energy diagram, but okay, it's same, but different. Okay. Um, Basically, it's saying again, for a hydraulic jump, right? The momentum is the same, but then like if you check, right? If you check the two depths in the energy, it's not the same. There is energy loss. Okay. So the depths that have the same momentum is called conjugate depths. Okay, so something that I want to emphasize, conjugate depths are different from alternate depths. Conjugate depths, same momentum. Alternate depths, same energy. Do not confuse the two. Okay, these two are two different things. Okay, so again, if you see the picture, right, one momentum corresponds to two depths. So basically, so basically, this is the depth before the momentum jump. This is the depth after the momentum jump. Okay, so you have this formula. This is the one that you need to memorize for rectangular channels. I won't cover for non-rectangular channels because one, it's rare. Two, it's tedious. Okay, so I will just cover rectangular, the most common one. So what the formula is saying, right? If you know the depth after the jump, you can know the depth before the jump. So you just input it to this formula, you get the depth, you get the other depth lah, basically. If you input the depth before the jump, you can get the depth after the jump. So the formula works two ways, okay? The formula works two ways. So I hope this is clear. Actually, that's everything for momentum jump. Sorry, not momentum jump, hydraulic jump, Okay, so 3A and 1 and 2 is actually the one that I showed you before. Define conjugate depths, same, depths with same momentum. Then sketch the momentum function and energy diagrams. Show the energy loss is exactly this one. Okay, this one just copy paste to the bottom. Okay, so this is the interesting part. This one, because this is taking too much time. I will go back to this. At this point, I will just describe the theory first. So if you remember, right? If you remember, this is slope. This is steep slope. This is mild slope. We have option one, which is you go hydraulic jump at a steep slope. Then you have S1. Okay. Sorry, before we can do this, I think it's better to go to the sluice gate first. Sluice gate. It's better to go to the sluice gate first. So for sluice gate, right? I want to clarify something about the formula. So this formula applies only right before and right after the hydraulic jump. It seems simple, but when you apply it, it's actually not, as in like, sometimes it's not that obvious, like the first time you study. So let's say you have a sluice gate. This is mild. Okay. So you know from the one before, right? This is M1. This is like M3. And this one is normal depth, right? So let's say this is Y1. This is Y2. This is YN, right? So the point that I want to make, right? The point that I want to make, YN and Y2 are not conjugate depths, okay? They are not. Why are they not conjugate depths? Because there's this M3 profile. So this, because if you notice, right, this is a bit deeper than Y2. So YN and Y2 are not conjugate depths. How do you find this depth? You find the conjugate depth of YM. So this is the Y conjugate. Okay? Because the hydraulic jump happens after the M3. Okay? So Y2 and YN are not conjugate. Okay, so I'll just write this down. So careful. Y2 and YN are not conjugate depths due to M3 because there's a slight increase, right? So how do you find the conjugate depth? Just apply the formula. So Y conjugate is equals to YN over 2 multiplied by -1 plus 1 plus 8 Froude number of the n squared. Okay. For the steep slope, it's also the same thing. Steep slope is also the same thing. So let's say you have a sluice gate, right? So you have this S3. This is hydraulic jump S1. So again, I want to emphasize, let's say this is YN, this is Y1. So I want to emphasize that Y1 is not the conjugate depth of YN. The conjugate depth is this one. Okay, be careful, okay? Y1 and Yn are not conjugate depths. You need to find the conjugate depth from the equation. So I hope this is clear. So conjugate depths are to find right before and right after the hydraulic jump, the water depth. Okay, so now let's go back to the case that I'm trying to tell. So let's say you have this, right? steep, this is M. So this is steep, S1, or you have M3, or jump. So this is the case that I want to, this is the thing that I want to emphasize. How do you know which case is, how do you know which case we are using? You have yn1. Okay, this is yn1. This is yn2. Okay. So how do you know that? So how do you check? So step one, you check y conjugate 1, which is basically just, yeah, just apply the formula to yn1. So this yn1 divided by 2, so -1 plus square root of 8 plus, sorry, 1 plus 8 fr n1 squared. By the way, fr is v square root of gy, just in case that you forgot. Okay, so you apply conjugate 1. So number 2, if the conjugate is lower than y normal 2, how to jump at steep. What do I mean by this? If you look at the diagram, right? If you look at the diagram, this conjugate depth, right, is supposed to be below the normal because we have S1 to increase the depth. So if it is really below yn2, then the hydraulic jump happens at the steep slope. So you get what I'm saying, right? I hope you get what I'm saying. So that's the case. So hydraulic jump at steep, because like it's according to your diagram. But then if your conjugate is above the normal, so in that case, right, we have like jump to this much, then it's not possible, right? It's wrong. I mean, like it's wrong compared to our diagram. So hydraulic jump happens at mild. Okay, so if it's at mild, then yeah, you need to find this one, this depth, which is y conjugate 2. Okay, I hope you get what I mean, right? So you find the y conjugate of yn1. If it's below yn2, right, then our diagram is correct. It will happen at s1. So this is wrong. But then if this is above normal 2, then it happens at the mild slope. So this is, so we take this hydraulic jump. So you guys get what I mean, right? I hope you guys get what I mean. I mean, you guys can do this question, I guess, but this is too long. Yeah, I cannot find the short questions. Should we do this? I think we should do this. Okay, why not? We still have, actually, right? This question you can try yourself. I think I will do the question on direct step method, because the direct step method is a combo of hydraulic jump, sketching, and direct step. So that's why. So I think I'll skip this question. I'll just directly go to this one. So this one, right? GVF, just now we just draw, right? We just draw. But if you want to find the exact, what's that? Let's say you have an M1, right? If you want to find the exact length and dimension, right? Basically, you want to find the exact calculation, right? You need to use numerical methods. The first one is called the standard step method. The second one is direct step. So for standard step, let's say this is M1. For standard step, right? You have, so given x, so let's say this is like, so we give the increments by ourselves. So this is 1, this one, this one, this one, this is 1. So for each point, we calculate the depth. So that's standard step method. For direct step method, we do the opposite. So given, right, let's say you know the depth at this point. So this is 3. No, let's say this is 10. So you set this point as 8, I don't know, 8, 6,
4, 2. So based on the height, you find the x, you find the lengths. Okay, for 10 to 8, right, you find this length. For 8 to 6, you find this length. 6 to 4, you find this length. 4 to 2, you find this length. So I hope you get what's the difference. So usually, right, in the test and quiz and everything, we only use the direct step method because it's easier. Okay, because to find delta x from y, right, it's easier than to find x from delta y. Sorry, to find delta y from x. But there's one condition, which is the channel must be prismatic. So as in, like, if it's rectangle, then it must be rectangle all the way. If it's trapezium, then it must be trapezium all the way. You cannot have, like, let's say you have this and then you have an expansion. If you have like something like this, yeah, if you have something like this, then you cannot use direct step method. You must use standard step. But usually it's prismatic. Usually we just use direct step method. So there are two formulas that you need to remember for direct step method. It's just this one and this one. Okay, this one is the rearranged form of Manning's equation. So if you notice, right, v equals 1 over n RH 2/3 s half, right? If you rearrange this, you will get this. So actually, it's not a new formula. You just derive it from Manning's. You don't need to remember. Okay, this one you need to remember, but just use your logic, I guess. As in, the change in energy, basically, right? So how do you gain energy? You gain energy from energy, right? Sorry, the water gain energy from gravity. So it depends on the channel slope, because the channel slope, right? The channel slope gives gravity. Then you minus it with friction, because friction gives friction, so loss in energy. So that's why it's SO minus SF. So E is E2 minus E1, X is delta X. Then if you rearrange, right, you get this. So actually, you just need to memorize, yeah, Manning's and this one for direct step method. This table I will show you now. So basically, what you need to consider, right, is just the average RE and average velocity. Just don't forget these two. Okay, anyways, I'll just show you now. So, okay, firstly, one condition which you must use the standard step method, prismatic channel. Okay, so that's done. So, okay, so I'm going to do this one single question for the hydraulics, but it covers like energy, hydraulic jump, direct step method, and yeah, everything in between. Yeah, it is. Okay. So that's why I'm doing this one. So yeah, let's do this one question. And I guess after this question, we can take a break before going to hydrology, because I think, yeah, it's been quite tiring, 2 hours, right? So okay. So sluice gate is regulate the flow. So we have a sluice gate. So you are given the, oh yeah, wait, let me change the wordings of the questions. So if the specific energy and flow depth just upstream. Wait. So you are given the sluice gate. If the specific energy and flow depth just upstream and downstream of the sluice gate are 4 meters and, okay, sorry, this is, ignore this one. Ignore this one. The English is very bad in this one, but it's a good question. Okay. So we have a sluice gate. So we have a sluice gate, right? Um, so you have the specific energy, which is 4 meters, and you have just downstream 0.7. So find the flow depth and velocity just upstream. So you are finding this. Okay, you're finding this. Y1. Y1 is not Y normal. Okay, I want to emphasize Y1 is not Y normal. Why? Because again, there's either M1, or there's like S1, right? So Y1 is not normal. Just to emphasize. Okay. Yeah, that's why sketching is important, because you know, wait, um, sorry, someone asked, is the channel being prismatic? No, no, no. The question asks one condition where you must use the standard step method, so you cannot use the direct step. Sorry, yeah, non. You're right. Thanks. Non-prismatic channel. Oops. Yeah. Okay, thanks. Sorry. So you okay? You can only use direct step if it's prismatic. So you must use standard step if it's non-prismatic. Okay. 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 Let's go back. So so yeah, y2 is 0.7. You need to find y1, and you need to find v1. Okay. So okay. So one thing that I want to say, if you have a sluice gate, energy is assumed to be conserved. It's actually, yeah, state any assumptions. It's there. Okay. So assumption, right? For sluice gates, spillways, and what's the other one? Weir. Yeah, we assume that energy is conserved. So assumption, assume E is conserved. So in that case, right, you can say that E1 equals to E2. So, okay, because none of them is critical depth, we must use the full formula. We cannot just use 3 over 3. We cannot just use 3 over 2. We must use y1 plus q squared divided 2 gy1 squared equals to. Okay, we are given E equals 4, right? So we can just directly go to. Okay, we can just. Okay, before this, right? We can find. So E1 equals E2 equals 4. So we can find Q, right? Because we know Y2. So E2 equals Y2 plus Q squared divided by 2GY2 squared. E2 is 4. Y2 is 0.7 plus Q squared divided by 2, 9.81, 0.7 squared. Okay. So 3.3 multiplied by 2, 9.81, 0.7 squared equals to Q squared. So therefore, Q squared equals to, no, Q equals to square root of that thing. I don't know what that thing is, but let's count. 3.3 times 2 times 9.81 times 0.7 squared. Q equals to 31.726 meters squared. No, this is Q squared. Whoops. I keep, oh no. So square root of answer 5.633. Okay, so we've gotten this. So we need to find V1, right? V1 and Y1. So maybe we can find Y1 first. So E1 equals to Y1 plus Q squared divided by 2GY1 squared. So you know E is 4. You know Y1 is, you don't know Y1. You know Q is that much. 5.633 to 9.81 Y1 squared. So you solve for Y1. You multiply everything by Y1 squared, I guess. What's that value? So 5.633 squared, 2 times 9.81. So it's 1.6173. Okay, so we have this. So y1 cubed minus 4y1 squared plus 1.6173 equals 0. So use your calculators. You'll get y1 equals 1 negative 4. You have 3.89, 0.7, negative 0.593. So of course you reject the negative. This is y2. So we take y1 as this one. So y1 equals 3.89. And of course v1 you just v1 equals What's V1? Q over Y, is it? Yeah, Q over Y. So Q is 5.633. Y1 is 3.89. So that's 1.45. 1.448 lah. I'll just make it more accurate, I guess. Done. So that's part one. So let's go to part two. So wait, I hope you guys get what I'm doing, right? It's basically just equating the energies. Okay. So yeah, just equate the energies actually. Okay, so we're done. So part two, if the normal flow depth is this much, normal flow depth is this much, calculate the distance downstream of the sluice skip where the hydraulic jump is formed. Now this is the fun part. Okay, so this is like, again, this is like combination of sketching and direct step method and hydraulic jump. That's why this is like a good question. So we have a sluice gate, right? We have a sluice gate. So first thing first, you need to know whether the slope is steep or mild. Why do we need to know? Because if steep, right, the hydraulic jump happens before the gate. If mild, the hydraulic jump happens after the gate, right? So in this case, right, you need to find the critical depth. So critical depth is Q squared divided by G 1/3. So Q is how much Q? Q is 1.448. Okay, so let's go. 1.448 squared, 9.81, 1/3. So we have 0.597, 598 meters. So we see the normal depth is 2.7, right? Hey, why is it very far? What the heck? Oh, am I right? I'm wrong. Q is 5.633, not 1.448. That's why 5.663 squared. 633. Oh gosh. Wait. 5.633. 1.479. Okay, this makes more sense. Okay. So we know that SY normal is bigger than YC. Because 2.7 is bigger than 1.475, 479. Slope is mild. Okay, so now that you know the slope is mild, we can draw the sluice gate. So we have the sluice gate. So again, because it's mild, you have M1. So if you notice that this is Y1, this is Y normal, this is Y2, 0.7, right? Then because this is mild, right? This is mild. We have M3 jump and then back to normal depth. Okay, so if you are interested in finding this one, right? You're interested in this one. The question asks for what's it? The distance from the sluice gate, right, to the hydraulic jump. Then we need to find this depth. So we can compare 0.7 with this depth and we can find the delta x. However, again, this is y conjugate, right? So how to find y conjugate? You use that one formula that I told you. 1 conjugate equals to, again, we are, so you what's it? You refer to the beginning and ending of the hydraulic jump. So the hydraulic jump ends at the y normal, right? So use the y normal as the y. So y normal divided by 2 square root of -1 plus 8fr squared. So we need Froude number squared, right? So I think we can find that one first. So I guess Froude number of the normal depth squared is v squared over gyn. So v, right? V is, we found v normal, right? It's not v normal, gg. So v is Q over Y normal, right? Wait a second. So we have, what do we have? Q squared divided by G yn cubed. So let's find it out. What's Froude's number squared? Q is 5.633 divided by G is 9.81. Y normal is, what's Y normal? What? 2.7. Okay, it's given, right? 2.7 cubed. 5.633 squared, 9.81, 2.7 cubed. So that's 0.1643. So that's Froude number. So we can go back to our conjugate depth. So 2.7 divided by 2. I think I'm missing something. I am missing something. Yeah, there. -1 plus square root of 1 plus 8 multiplied by 0.16433. Okay, so you can just calculate this. 2.7 divided by 2, -1 plus square root of 1 plus 8, 0.16433. 0.7038. Right? So now the setup is ready. We need to find delta x. Right? Delta x. But then the question asks for one step length. One step length. So what does that mean? As in, like, so let's say you have two depths, right? You have two depths. One step length means you just compare this directly. You find this loop. Two step lengths means you get the average. This is one step. This is second step. So you find the slope of this, find the slope of this, find delta x1, delta x2. Three step length means you divide it to three. I mean, yeah, you get my point. You get my point. Let's say you have this, this, and this. So 1, 2, 3. But in this case, the question only asks one step length, right? So we can just compare directly. So let's do exactly that. So we want to find the delta x from 0.7 to y conjugate. So let's make a small table. So okay, direct step method. You are given y. Y is from 0.7 to 0. How much? 0.7039, right? What do you need to find? Okay, let's go back. S equals, wait a second. V equals 1 over n RH S half. So SF. So SF equals to NV over RH 2/3 squared. So we need N. Okay, we need N, V, and R. Okay. So let's find RH first, I guess. Wow, this is very tedious. Wait, this is a white channel, right? No, it's not. Is it? No, it's not white. Okay, shoot. So we know that this is Y. This is, oh, no, never mind. You may assume that the channel is wide. Oh, lucky. And Manning's roughness is 0.33. Okay, so we can assume the channel is wide. So Y is, okay, so let's continue. So RH, because channel is wide, so we can approximate it as Y. So 0.7, this is still the same. V is Q over Y, right? So let's calculate this. So Q is 5.63. So divided by 0.7, let's try. You get 8.047. Then you divide it by 0.7039. Let's see what you get. You get 8.003. Okay. So you found this one. What to do next? You need to find the average. So average of RH, right? You just average 0.7 and you just average this basically. 0.7 plus 0.7039 divided by 2. You get 0.70195. Average the velocity. You get 8.047 plus 8.003 divided by 2. 8.025. Okay, now that you have the average, wait, somebody asked, why is the conjugate depth higher than y0? What's y0? You mean 0.7, is it? Our normal depth is this one. We have mild slope, not steep slope. 0.7 is not normal depth. Okay, our normal depth is 2yn. This is mild slope. We are just forcing the flow to go to 0.7. Yeah. So yeah, I mean, so this is correct so far lah. Yeah. Okay, so we have this. So we have the average RH, we have the V. So we can find SF, right? So we can find SF. So what's SF? Yeah, just input into this formula. So, oh geez, with SF NV over square root of 2/3 squared. Okay, so N is 0.03, right? So you input 0.03, 8.025. Yeah, just input the numbers. 0.03 times 8.025 divided by hydraulic radius, which is 0.70195 to the power of 2/3. Oh wow, okay. To the power of 2/3, you square the number, you get SF, which is 0.0929. 0.0929. Okay, now you get SF. How do you find SO? SO is our bed slope, right? So you need to use Manning's. Oh wow, Manning's of the normal depth. Okay, so SO. Okay, wait, I'll just write this here. So SF N V R H 2/3 squared. SO N V, is it V? Yeah, V of the normal depth. Yn 2/3 squared. V at normal depth, by the way. So you know that the normal depth is normal depth. How much is normal depth? This is normal depth 2.7, right? 2.7. So you include, so this is, so 0.03. V is just Q divided by what, right? So 0. Okay, 5.633 divided by normal depth 2.7. Then you divide by normal depth 2.7, 2/3 squared. I know this is a lot of work, but this is something that you need to go through. 8 marks, eh? What the heck? Very little. 0.03, 5.633, 2.7, 2.7, 2/3. So it's squared. So you get 0.001, is it? Yeah, 0.00104. I hope I am writing this correctly. Okay, so we have SO. So what else do we need? Oh yeah, so delta X equals E2 minus E1 divided by SF minus SO, right? No, SO minus SF, sorry. Okay, so E2 is this energy. We don't know, so we need to calculate again. So 0.7039 plus V squared over GY, right? G is 9.81. 0.7039 minus, I think E1 is given, right? From the one before. E1 is 4. Yeah, see, E1 is 4 because it corresponds to 0.7. So minus 4, all divided by SO, which is 0.0014. So 104, sorry. Minus 0.0929. Okay, a lot of calculator punching. Oh, geez. Okay, 0.7039 plus 8.003 squared, 9.81 times 0.7039. Okay, I got the wrong answer. I am, wait, did I put it something wrongly? I forgot to square this one, sorry. That's why. Okay. Still wrong. What the heck? Oh no. Where did I get this wrong? Okay, I'll just copy paste what I did, I guess. Again, I'll copy paste what I did. NTU, SEM3, CV2020, it's Q&A. Wait, no, PY, no, Q&A. I think it's Q&A. Okay, so this is the exact same question. So where did I get wrong? Okay, maybe the energy I get wrong. Yeah, so you will get 0.344 by right. So yeah. I know, right? How is this part only worth 8 marks? It's really oh GG. I think SO is SO correct. I think with SO it is 1.04 times 1. I think I'll copy this. Okay, copy. I hope this paper this question worked more. Okay. Hey, no, I wait. Sem 3. Okay. I guess after this part we can like take a rest. As in um we will take a rest for I don't know 5 minutes, then we go to hydrology. But oh wow, this much calculation. That's too much, man. Okay. Let's paste. Okay, let's check. Let's check which is wrong. So we've gotten the 104 correct, right? So 1, 2. Wait, this is like 1, 2, 3, 1.04. Yes, it's correct. So 0.0929 is correct. So it's the E2 is wrong. So my E2 is wrong. Something wrong with my E2. E2 is Y plus V squared over GY, right? Wait, is it? 2G. Oh, oh wow, okay. Whoops, guys, this is 2G. 2G. Okay, we found the answer. Nice. Okay, let's redo our calculations. Okay, 2. So 0, yeah, finally, woohoo, 0.345 meters. Done. Oh wow. Okay. So basically, right? So sketch and label the water surface profile. We've done it, so we don't need to care anymore. I mean, just change these two numbers. So yeah, show that the hydraulic jump occurs very close to the sluice gate. So I mean, 0.345 is just how many centimeters? 34 centimeters, right? So it is correct. Okay, so I guess we'll take a break for 5 minutes. So come back at 15:47. We'll continue with hydrology. The rest of the questions you can try yourself, but oops, sorry. I just want to show that. See, if you see, right, this is sketching. This is sketching. Critical and normal flow. This is like uniform flow and energy, right? And then you have the possible water profiles. That's again sketching. And then hydraulic jump. And then what's that? Distance between intersection reaches 2 and 3. That's direct step method. So if you notice, right, 19 marks is like a combination of everything from hydraulics. So yeah, you better like learn everything. Like for hydraulics, you really cannot separate into parts, man. So that's the hard part about hydraulics. Yeah, so okay, let's take a break for 5 minutes. Okay, maybe I can answer like people asking also. So okay, somebody asked about the hydrograph. Okay, flow duration curve. I think it's actually I'm not sure because I know some syllabus are removed, so I'm not sure what flow duration curve is. Yeah, it's something that we haven't learned. So don't worry about flow duration curve. Yeah. Yep. So maybe for the ones that are still here, you guys can ask questions or take rest first. Yo guys, I'm back. Okay. Um, okay. And then synthetic unit hydrograph, we also haven't learned. Synthetic unit hydrograph is like, I mean, I've read a little bit about it. So hydrograph, right? We base it from past data, right? Synthetic unit hydrograph, we don't base it from past data, but we haven't learned. Yeah. Chill out. From I don't have a Kit Kat. Well, okay. Okay, guys. I mean, okay, sure, break. I mean, good thing, right? As in, like, this is my review also. As in, like, I'm taking this also, right? I haven't done that much past paper, so this is like my review, I guess. Um, Wait a second. Let me check.
Okay, you guys ready? Okay. Um, okay, I'm ready. Okay, let's go. So I guess I'll take, I don't know how long. This is my review anyways. Our review lah. Okay. So I guess we can go to, okay, so actually we've done with everything from hydraulics. You just need to memorize normal flow, um, the one about the momentum equation with the Froude number thing, direct step method, the sketching, specific energy. Yeah, that's everything already. So I guess we can go to hydrology. So for hydrology, unlike hydraulics, you can study like one part by one part, because like it's like not everything is related. In hydraulics, everything is related, so you need to master everything. For hydrology, it's not. so that's a good thing. So this is everything. I've listed everything here. So
So this one never comes out in the past paper, and I don't think it's that important. So if you guys are really want to like last minute effort, just study these 3 chapters. But even this is quite rare, and it's already out in the quiz, right? So I think it's probably going to be like these two. So yeah, um, so we have hydrograph shapes, velocity area. Okay, actually, I'll just go through. I'll start from I'll directly start from hydrograph analysis because I believe you can like read this by yourself. As in like, I mean, if you have time, we will do questions, but I guess I'll. So unlike hydraulics, right? I think I won't explain much because I think the lecture slides has already presented it very well. What I will do instead is just apply it to the questions directly, because hydraulics different. Hydraulics, I know like most of you are still blur one, even I was blur until like a few days ago. So so but for hydrology I think it's better. So I'll just go straight to the questions. So again, this one I don't have any notes because just refer to the lectures. But for surface runoff, right? I will just go. What's it? I'll just slide through. So this is everything that you need to know from hydrology. So when I scroll right and you don't know anything, and then like I mean like this is just for you to know what you don't know. Basically, this is like a checklist lah. Basically, so this is river discharge. So this is reservoir capacity design. So yeah, so this is one of the questions. This is like river. Again, I will skip to hydrographers because I think that's more important. But this is the river. This is the reservoir design, and this is the river. So yeah, so again, hydrograph analysis. Again, I'll just skim through everything, just see what you don't know. So first off, in hydrograph analysis, there's actually quite a lot. So first thing is finding the end of surface runoff. So you can use the logarithm method or the QT over QT plus N method. You have the separating the runoff base flow. I think this is the most common question, and I think this is like the most important out of everything. Like at least you must know how to do this, like separating the runoff and base flow. So again, we have like constant slope, constant base flow, convex and concave. Then we have constructing unit hydrograph from past data. The key that I want to take note is just do not forget to scale down. So you need to find the depth of the past data. Okay, so yeah, so whoa, okay. So this is the past data, and you need to construct the unit hydrograph. See, past data, you convert it to base flow. You convert it to direct runoff, and you convert it to unit hydrograph. Then you have multiple hydrographs. You need to average. You have multiple unit hydrograph. You need to average them. Just don't forget to change the peak. So the first thing that you need to do is to find the average peak flow and average time to peak, and just put it there. Okay. Then we have this one, constructing a new unit hydrograph out of another unit hydrograph, but integer multiple. Okay. Again, I'll just skim through. If there's the question, then I'll do this. But if there's none, then okay lah. Then we have the S curve. S curve is for, was that non-integer multiples? So just now this is like integer multiples, right? For non-integer multiples, you use S curve. So this is S curve. Yeah. Then we have the application. Yeah. So again, just don't forget to scale down in the end. So this is the what's that? You take the difference. Don't forget. Yeah, this is like the difference, and you plot the difference. Yeah, that's why you have like S minus lag S curve. Okay, this is the superposition and proportionality. So you have this one, you have the unit hydrograph. You want to use it to predict real rain. So unit hydrograph is a model. So you use the unit hydrograph to model or predict real rainfall hydrograph. So you have proportionality and superposition. Then yeah, these are the questions. So yeah, let's go to the questions. Okay, so we have a recorded hydrograph from a 432 kilometer squared catchment, 2 hours net storm, no direct runoff from days 1 to 2 and days 10 to 12. So find the hydrograph, sorry, separate the hydrograph into direct runoff and base flow, concave method. So let's do that. Okay, so the hardest part of hydrology is converting what the lecture teaches, the one which is in pictures, into tables. That's the only part, that's the only hard part with hydrology. But once you know how to do it, the questions never change. Like the questions are consistent. Like if you see the past paper, I think number 2 is always river, number 3 is always hydrograph, number 4 is always the routing. So it's always consistent. Anyways, so concave method. So if you remember, concave method means, let's say this is your hydrograph. Concave method, right? So it means, what's concave method? You have this, right? And then you draw up to the end of the base flow. Okay. So yeah, this is time. This is discharge. Okay. Okay. Wait a second. There. So this Q, that's time. So this is the direct runoff. Runoff. This is the base flow. Okay. So for concave method, you just need to draw this line, extend it to the peak, and go back up. Okay. So again, the hardest part is to convert this drawing into the table. So actually, right, you don't need any drawings. Like for your answer, you don't need any drawings, but the drawing will help you a lot. So I recommend to draw. So we have what? Let's construct a table. It's a very bad, very bad line. We shoot. So this is day. So we have 1, 2, 3. How many days? 12. Oh, that's a lot. Day, and then we have flow. Then we need to find the base flow, right? We need to find the base flow. So and then we need to find runoff. Okay. So flow is 8, 7, 12, 25, 52, 90, 56, 40, 32, 23, 16, 12. Okay, so we need to find the base flow. So again, with the concave method, we have these 2 lines. So how do you find the base flow? Use y equals mx plus c. So again, so we have 1.1 is 1,8, right? So this is 1,8. This is what? 2,7, right? So you need to connect this to the peak. Let's see where the peak is. The peak is at the number 6. See, this is the peak. It has the highest flow. So this one is the peak. Okay, so we need to find 6 comma how much. So I mean, this is a straight line. We can approximate it as a straight line. So of course we can use y equals mx plus c. So let's do exactly that. So first line. So y equals mx plus c, right? So y minus y1 equals m x1. Okay. So y equals y minus 7. M is 7 minus 8 divided by 2 minus 1. X minus 2. Okay. So this is, we're just basically finding the equation of line. So y minus 7 equals how much? Negative 1, right? So yeah, so we have y equals negative x plus 9. What the heck? Okay, so this is the equation of this line. Okay, so that's the equation of that line. So of course we can find this point, right? So that's 6 comma. So at x equals 6 comma y is -6 plus 9, which is equals to 9 minus 6. So that's 3, right? So this is 3. This point is 3. But 690 is here. 690 is here. Okay? But we are interested in this point anyways. So 63. Then we need to find the equation of the second line. So again, the second line usually ends at where the direct runoff direct no direct runoff ends. So direct runoff ends at the 10. Okay, so this is the 10. This is the 10. We don't know the y. So again, we go to the second line. So second line. Okay, so we find the equation of line. So we have y minus y1 equals m x minus x1. Sorry, we know 10 equal. This is 1023. Right, this is 1023. So y minus 23 equals to m is 23 minus 3 divided by 10 minus 6 x minus 10. Okay, so so y minus 23 equals to, bring out your calculators, that's 20 divided by 4 actually. Yeah, so it's 5 x minus 10. So you have y equals to 5x 23 minus 50, right? -27. Okay, so now you have these two line equations. Okay, we have two line equations. The first one is this one. The second one is this one. So what do we do with this? Well, you know that the base flow is the one that is below the line, right? So we can find the base flow by, yeah, but just by plugging values here. So x, right? I set x as the number of days. So x is number of days, right? So just plug in x equals 1, x equals 2, x equals 3, x equals 4, and so on. So x equals 1 is supposed to be 8, 7. This is supposed to be the same, right? So now let's find day 3. So day 3, right? So just find, actually this, for this one, right? I think it's better to show you the calculations. Okay, yeah. Okay, now that's better. So we just plug in. Actually, right, for this one, you can use table. I don't know how to use table in, wait, mode. Oh, there it is. Table. So fx equals, I want negative x plus 9, right? So negative. Okay, so for hydrology, familiarize your way to, yeah, familiarize you, was it? Just use your calculator, basically. Just try to use your calculator. So start, I want to start from 1. I want to add at 6, right? Step equals 1. There it is. So 8, 7. Oh, 6, 5, 4, 3. Okay. 8, 7, 6, 5, 4, 3. So this one is basically equation of line 1. Okay. This is line 1. Okay, first line for this first line. The rest, right? Because we are interested in base flow from 6 to 10, right? So 6 to 10 is this. So this second line. Okay. So mode. So yeah, by the way, guys, if you want to try to your calculator, so go to mode, click table. You have this fx, right? Input second line is 5x minus 27, right? So 5x minus 27, then equals gx, just ignore. So you want to start from 6, right? So start from 6 and at 10, step by 1. So you get this table. So 6 is 3, 7 is 8, then x equals 8, y equals 13, then y equals 18, this is 23. Now you have this base flow, so you're done. Yeah, so, and then of course, we assume that the base flow after this point, right, is all base flow. So this is just copy paste. Okay. Then for runoff, then we just minus. So 8 minus 8, so flow minus base flow. So runoff is just a flow minus base flow. Because, okay, again, inside the table, right, you want to find this area. how to find that area? You minus the whole, you have the whole thing, you minus it with the base flow, you get the runoff. So again, it's just a matter of translating your graph into tables. So again, this is just 0, 0, 6, 20, was 52 minus 4, 48, 87, yeah, 56 minus 8, that's 48, 40 minus 30, 27, 32 minus 18, 14, then 0, 0, 0. So done. So this is your final answer. You don't need to plot. You don't need to plot. So it's that easy. You just need to know what you need and what you don't need. Okay. So part 2, based on the direct run of hydrograph, determine the 2-hour unit hydrograph. So this is our next step. Okay. So we need our unit hydrograph. So how do you construct a unit hydrograph? Please review if you don't know yet, because I won't be explaining too much, because you can just literally just read the lecture slides and review. I don't think there's enough space in this page. I guess I need to add a new page. Whoa, okay. No, okay, fine. Copy and paste. Hey yo. Okay, so this is the runoff. So we need to construct a 2-hour unit hydrograph, right? Yeah, 2-hour unit hydrograph. So firstly, we check. So this is 2-hour unit hydrograph. We have 2-hour rain. So basically, we don't need to do any of the S curve. We don't need to do any of the, the addition of hydrograph, because our rainfall is already equal to the hydrograph that we are interested. Oh yeah, by the way, just to clarify, okay, just to clarify, because I think some of you are still confused. 2-hour unit hydrograph, okay, 2-hour unit hydrograph means that the rain is effective rain is 2 hours. Doesn't mean that the hydrograph is 2 hours, okay? You get what I mean? So as in like, oh, how do you draw it? Okay, so let's say you have hydrograph, right? So for 2-hour unit hydrograph, this is 2 hours, but doesn't mean that the whole hydrograph is 2 hours. No, this can be like, I don't know, 10 hours, 12 hours. But yeah, basically what I'm saying, right? The rain is 2 hours, not the hydrograph. Okay, don't get that wrong. I mean, this is just for theory questions lah, but what's it? Knowing the professor, I think he likes to do theory questions. So yeah, just be careful. Actually, right, we can convert this to time. Then we convert this to, sorry, wait a second. Time in days, and it is run off. Wait, is it day, right? Hey, that's day. Wait a second. Okay, never mind. So we have day, we have run off. So for unit hydrograph, right, we start when the runoff starts. So you ignore the zeros, you convert this to 1, 2, 3, 4, 5. Yeah, you only consider the one that has runoff. So what else do we need? What else do we need? Okay, so we need to find the total runoff. So total runoff. How much is total runoff? Again, use your calculator. I know you can just plus it one by one, but it's way nicer if you use stats, data. Wait. Okay, actually this is different from my calculator, so I'm not sure. I'm not sure how to use this. It's different from the calculator that I usually use. Okay, but basically 0, 6, 20, 48, 87, 48, 27, and 14. Okay, so what's that? AC, shift, stats, um, one variable. Wait, what the heck? No, shift, stats, one variable calculate. There it is. Well, okay. So we find the, okay, total X is 250. Yeah, so again, utilize your calculators. It's very important. So learn how to use your calculator. So for the ones that use the same one as mine, you can go to mode. You go to mode, you go to stats number 3. So I don't know if you can see it. So basically go to number 3, that stays stat. So this one, stat. Then go to one variable. Then you have like this table. I don't know if you can see. You have this table, right? Then you just input all the numbers. So by the way, this is useful for probability and statistics also. So yeah, just learn how to use your calculator. Yeah, but basically I just skip lah. Basically we got the total runoff 250. But then 250 watt, right? 250 watt. Runoff is in meters cube per second, right? Let me check. Yeah, so it is in meters cube per second, but we are given days. Okay. And then we have the area with 432 kilometers squared. So let's go back. Area is 42 kilometers squared. We have total runoff of this much. So how much rainfall do we have? Well, we test. So we see. So effective. So how many effective rainfall do we have? Effective rainfall is, we have this much runoff. For how many days, by the way? For 7 days, right? For 7 days. So we find the volume by this one. So 7 days divided by the area of the reservoir, or whatever it is. Yeah. So yeah, wait, let me go put this down here. Okay. So we have that. So yeah, convert the units to the right one. So 250 meters cube per second. Actually convert this to hours actually. So 250. We want millimeters per hour, right? Sorry, we want millimeters. We want millimeters. If you want millimeters, then times 10 to the power of how much? 6, right? No, 9. Yeah, divided by seconds. Okay, this is seconds, so 1 second times. Okay, wait. Okay, wait. So this is in, now this is in millimeters cubed per seconds. You multiply by 7 days, so that's 7 times 24 hours times 3,600 seconds. So this seconds already divided by 432 times 10 to the 12, 10 to the 12 millimeters squared. Is it? So kilometers to meters is 10 to the power of 3, to the millimeters, that's 10 to the power of 6 squared, so 12. Yeah. Okay. So effective rainfall is, let's calculate. So 250, 10 to the 9, 724, 3,600, 42, 10 to 12, 350 millimeters. Okay. So we've got this. So that's our effective rainfall. But then remember, we want unit hydrograph. So if it's a 2-hour unit hydrograph, so we want, wait, do we divide the intensity or do we divide the volume? I think it's volume, right? Okay, basically, if you want, because unit hydrograph, right, we want 10 millimeters. Wait, okay, guys, let me check. Is it the volume or is it the intensity that we divide? Oh, yeah, it's the depth. Okay, never mind. I'm right. Okay. So, okay, let's go back. Sorry. Okay, so unit hydrograph, right? We want 10 millimeters, right? So scaling factor is um 10 divided by 350. So that's, what's that? Okay lah. I mean, I'll just leave this as 1 over 35, I guess. Okay, so that's our scaling factor. So let's go back. Um, let's go back to our table. Okay, let's go back to our table. So we have run off, right? We want the unit hydrograph. So we want the unit hydrograph, right? So unit hydrograph in meters per is this one. So basically this one, right? It's just run off times scaling factor. So multiply everything by 1 over 35. So 6 divided by 35. Um, Taking too much time. 0.17171. Wait, by the way, correct me if I'm wrong. Because honestly, I haven't really seen the, what's that? The solution. Actually, I want to check actually. Wait, let me check for a bit. Hydrology 1718 SEM 2 for C. Is it there? No. Ah, okay, interesting. Anyways, okay, let me check. Let me check the example. Sorry. Okay, so we have direct runoff, right? Because we've separated base flow and direct runoff, so we just need this step. Ah, okay. They adjust the time. Um, okay, they adjust the time last. I see. I see. I adjusted the time in the beginning, the one that I mentioned. Ignore the zeros, if you remember. Okay, but it's the same thing. Okay, so we have time, but remember that the time is still days. Okay, don't get confused. I know the unit hydrograph is, was that 2 hours, but that again, 2 hours means 2 hour rain. Doesn't mean that the hydrograph must be in 2 hours. Okay, so let's go back. So 20 times 1 over 35. Okay, this one, yeah, you guys can help me. It's taking a lot of time. 0.571, then times 48, 1.371, then times 87, 2.4486. Actually, I'm not sure how many significant figures you are supposed to write. So I don't know. I just write whatever. Yeah. So this is your unit hydrograph. So that one question is done. So I think for strategizing, right, for the test, right, I think it's better to do the hydrology first, because I mean, look at this. It's more marks than the one that we did before. The one with the, the one with the, what's that? The one with the direct step method and hydraulic jump combined. It's only 8 marks. This is like 9 marks. What the heck? Okay. Anyways, yeah. So again, that's unit hydrograph. Let's see the next question. So this is the one which have the, what's that? Superposition and proportionality, because you need to see. So construct the discharge hydrograph. So this is like predict the hydrograph from the unit hydrograph. Yeah. So I'm not sure if I want to do this because I think I mean, all of the questions are similar lah, but I think let's find S curve. Let's find S curve. I mean, this is QT over Q2 plus 1 ratio. Um, yeah, so yeah, let's do S curve. Let's do S curve. Let's do S curve. So okay, so this is a 2 hour unit hydrograph. We want to find the 3 hour unit hydrograph. So because this is not integer multiples, you must use S-curve. So again, let's just let's construct the S-curve. So to construct the S-curve, you need the, so this is the time, this is the UH, 2-hour UH. This is the addition to S-curve. This is the S-curve itself. Okay, so time 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2-hour unit hydrograph, so it's 0, 43.4, 72, 59.8, 36.8, 18.2, 12.6, 0. So addition to S-curve, this is a 2-hour hydrograph. So 0, 0. Then for addition, right? You add. So okay. So this is like time equals 2, right? So you add this one, like, what's that? You go back. You go. Okay, this is a 2-hour unit hydrograph, right? So you go back 2 hours. You add these two up. So this is 0. Okay. So again, for this one, right, you go back 2 hours. You add this up. So this is 43.4. Okay. Next up, we go back to hours. So this one, you add up this one, 72. So again, this one, you go back to hours. So 5, you go back to 3. You add up these two. So that's 59.8 plus 43.4, 103.2. Okay. So for time equals 6, you go back to this one. You add up these two, 36.8 plus 72, 108. Whoop. 108.8. Okay, this one again, go back to hours. So 18.2 plus 103.2, 121.4. Okay, this one again, go back to hours. I mean, this is 0 lah. Let's assume 0. Okay, so what's that? 108.8 plus 12.6, 121.4. Okay, so at this point, it's constant lah. Okay, so we can stop here. So for the S-curve, right, you just add horizontally. So 0, 43.4, 72, then 59.8, 43.4, 103.2. So yeah, add horizontally. So 72, 36.8, 108.8. Okay, there's no fast way of doing this besides Excel. But apparently this is what you need to do in the exam. So yeah. Okay, so we have our S-curve. So we need to find the 3-hour hydrograph, right? Okay. So we need to continue the table. So we have the S-curve now. So what we need to do, we need to find we need to lag S-curve. So lag S-curve by how much? 3 hours, because we are interested in 3 hours hydrograph. So this by 3 hours. So okay, lag S-curve by 3 hours. So okay, let's just do exactly that. So 0, 0, 0. We start at 3 hours. So this is 0, 43.4. Wait. Yeah, it is. Why am I confused myself? Okay, so 0, 43.4, 72, 103.2, 108.8, 121.4. Actually, wait a second. I want to check a little bit, just in case I'm wrong. With okay. So for 6 hours, you want to find 2 hours, right? So you need to lag it by 2 hours. So this is like X curve. So yeah, it's correct. Okay, nice. Okay, sorry for a lot of scrolling, but okay. So like S curve by 3 hours. So you need to find what? Um, so S curve minus lag. Okay. So S curve minus lag. I simplify this S minus lag just to make it shorter, I guess. So 0, 43.4. This is 0, 0, 0 actually. Okay. 72, 103.2. 108.8 minus 40 was it? 108.8 minus 43.4. 65.4. Then 1 to 1.4 minus 72. 49.4. Then 1 to 1.4 minus 103.2. 18.2. 1 to 1.4 minus 108.8. 12.6 and 0. So we have S lag, S minus lag. So in the end, right, we just need the 3-hour unit hydrograph. So how do you find this? How do you find the 3 hours unit hydrograph? You need to scale down. So scale down the S minus lag by how much? It's T1 minus T2. So scaling factor is T1 divided by T2. So that's 2 hours, right, divided by 3. Yeah, this is our scaling factor. So multiply everything by 2 over 3. Okay. Do you any of you guys know like the fast way to do it with calculator? Because I don't seem to find one, which is annoying. So you need to like manually input everything. So this is 28.9, then multiply by 72, that's 48. And multiply by 103.2. Okay. Yeah, but you get the point, right? I hope you guys get the point. Yeah, so this one, 49.4. Okay, so done. So this is your answer. So basically, you don't need to draw. You just need to find the table. Add to S curve. So okay, so there are a few methods. So okay, so graphically, you know that S curve is like this one, right? So you have like multiple unit hydrograph here. Then you add them all up. So there's a fast way of doing it, which is using this addition to S curve. So actually, this is in the lecture, but I'll go through this a bit. So you have the 2-hour unit hydrograph, right? So you want to construct the S curve. So yeah. So addition to S curve, how to say it? Okay, so this is 2 hours unit hydrograph, right? This is 2 hours unit hydrograph. So you need to refer 2 hours before. Okay, initially you start with 0. Okay, initially you start with 0 because you cannot refer to anything. What? Because there's nothing what's it? There's nothing before it, right? Okay. So again, so we start with, so this is 0, this is 0. Then let's start with this one. So we refer, because this is a 2-hour unit hydrograph, our addition to S curve. Okay, look at the time. The time is 2, right? So you refer 2 hours before. So you have time equals 0. Then you add up these two. You get, of course, 0 plus 0 is 0. Okay. Now let's see time equals 3. So we are focusing on this column, right? So time equals 3. So again, this is 2-hour unit hydrograph. So you need to refer minus 2, which is time equals 1. You add these two up, that becomes 43.4. Okay. So now we are in the fourth column. Time equals 4. You minus 2. So you go back to time equals 2, right? You add these two up, you get 72. Okay, so now let's go to time equals 5. So you go back 2 hours, you add these two up. So it's 59.8. plus 43.4. That's 103.2. Okay. So again, now we're at the sixth column. Okay, this is a 2-hour unit hydrograph, so we need to go back by 2. So it's time equals 4, right? So we add these two up. So 36.8 plus 72, that's 108.8. Okay. So we are now at the seventh column. So go back by 2 hours. We add these two up. We get 121.4. Okay. Next up, we are at the eighth column now. We go back by 2. Yeah, so we add up these two. So it's 12.6 plus 108.8. You get 121.4. So yeah, that's how you addition of S curve. To find the S curve, you just add these two up lah. Yeah. So I hope that's clear. Yeah, it's basically just knowing what you need to do. there's not much variation, unlike hydraulics. Okay, so next one, predict the discharge. So this one is the principle of superposition and proportionality. So let's see. Predict the discharge of this hydrograph given this 6-hour duration storm. Okay, 6 hours, intensity of 15. So what do you need to do? Firstly, draw the rainfall. I think it's better to draw the rainfall. So you have a 6 hours, right? So first 3 hours, intensity 15. Second hour, intensity 10. So you have 15, 10. Okay. Then you have constant loss of 5 millimeters. Okay. You have a constant loss of 5 millimeters per hour. You need to find the discharge hydrograph. Okay. So okay. So first things first, what do you need to do? Okay. Okay. So again, you have the 3 hours unit hydrograph, right? You have the 3 hours unit hydrograph. Remember that unit hydrographs only focus on the effective rainfall. Okay. So wait a second, let me check. Yeah, sorry. So in the first hour, we have effective rainfall, right? So effective rainfall. In the first 3 hours, we have effective rainfall of 10. In the second hour, we have the effective rainfall of 5 millimeters per hour. Okay, next, we know that unit hydrograph is always assuming that intensity is, okay, so for unit hydrograph, the intensity is wait, sorry. So intensity is 10 millimeters. 10 millimeters is a fixed number. Oh yeah, by the way, I know a lot of you get this wrong in the second quiz. It's 1 centimeters, 10 millimeters. It's not 1 millimeters, okay? I know some people get this wrong. Okay, it's 10 millimeters. It's 10 millimeters or 1 centimeters. But I prefer to remember it as 10 millimeters. Okay, do not get this wrong. So we know that the unit hydrograph always assume 10 millimeters of rain. But because this is a 3-hour unit hydrograph, right? 3-hour unit hydrograph that we have, the one that we have. So we divide it by 3. So we have 10 over 3 millimeters per hour, right? So now you have this tool. So you have like, this is your 3 hours unit hydrograph. You know the intensity of the unit hydrograph. So how do you predict this rain? How do you predict this rain? Again, we use the principle of proportionality and what's that? What's the other one? Superposition. Yeah, superposition. So let's do time. Okay. So time, right? We have 0, 1, 2, 3. Okay. I mean, we refer to this. So 0 to 7, right? So 0 to 7. So let's just show it. I don't think it's a. I think I need more space. Wow. Okay. Where is the? Oh, there. Okay. I didn't expect the question to take this long. By the way, I really didn't expect this. Oh wow. Okay. Okay. So we have time. This is in what? In hours. Okay. In hours. Okay. So first 3 hours we have effective rainfall of 10, right? So for direct runoff, wait, I know how to do this. I just don't know how to present it nicely. Oh no. So direct runoff, right? So direct runoff. Okay, I think I'll show it graphically first, okay? So we have 3 hours unit hydrograph. So what can we do? So for we overlap. So we have this rain, right? This first rain, which is 10 millimeters per hour. So we have this first unit hydrograph. Sorry. So this is our unit hydrograph. You want to multiply it by how much? Multiply it by 3. Why 3? Because okay, so unit hydrograph is 10 over 3 millimeters per hour. How do you get from here to there? You need to multiply by 3. Okay, so this is 0. Now time equals 3. We have another hydrograph, which is our 3-hour unit hydrograph. You multiply by how much to get 5? You multiply by 3 over 2. Am I correct? Am I correct? I'm correct. Okay. so 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 your 3-hour unit hydrograph, right, have intensity of 10 over 3. Your real rain have an effective rainfall intensity of 5. So to get here to this, you need to multiply by 3 over 2. Okay, and then because our second portion, right, starts from 3, so your next hydrograph starts from 3 also. Okay, the first one starts from 0 because the rain starts from 0. So yeah, so this is graphically, and then we just add up everything. We add up the y coordinates what's it, of the two curves. Okay, so this is q, this is t. This is still direct runoff, by the way. We haven't considered the base flow. We will consider the base flow last. Okay, this is still direct runoff. This is time, which is hours. This is meters cube per second. Okay, so let's do this. So I guess okay, I don't know how to make the nice heading, so I'll just do this. Okay, so this is referring to this one. Okay. Okay, so um okay, actually let me bring my 3 hours unit graph down so we can see. Copy and paste. So this is again our 3-hour unit graph multiplied by 3, right? So you multiply everything by 3. Okay, so okay, this one 3 times 3-hour unit hydrograph. Okay. So 0. And then what else do we have? Wait, actually, oh, never mind. Okay, okay, never mind. Yeah, just multiply this by 3. So 28. So 28.9 times 3, that's 86.7. It's all this boring calculator mashing. 68.8 times 3, 206.4. 430.6 times 3, 130.8. We have 32.9 times 3, 98.7. Wait, is it correct? 0. Okay, yeah, I'm just checking. So 12.1 times 3, 36.3. 8.4 times 3. Oh, this is taking a long time. It's 25.2. 0. Okay. So we've gotten our black curve. Now we just need our blue curve, which is this one. So blue. So 3/2 times 3-hour unit hydrograph. So again, remember that we start at 3 for this one. So this is 0, 0, 0. We start at 3. So wait, sorry, this time 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is the time, right? Because we are shifting it by 3, so we add everything by 3. So 3, 4, 5, 6, 7, 8, 9, 10, 11. So yeah, the 0 corresponds to time equals 3. So this is 0. 28.9 corresponds to times equals 4. So 28.9 times 3/2. I think it's easier if I'll do this. 43.35. Okay. Then we have 48 times 3/2, 72. Then 68.8 times 3/2, 103.2. Now we do this one, 43.6. 43.6 times 3/2, 65.4. Where I'm at, 32.9 times 3/2, 49.35. Then 12.1 times 3/2, 18.15. Then 8.4 times 3/2, 12.6. Then we have 0. So time equals 10, time equals 11. Okay, so we have this, right? What do we need to do last? Of course, we just need to add. So we just add everything. So this is our predicted hydrograph. But not yet, by the way. By the way, remember that this is only direct runoff. We haven't considered the one that we haven't considered the base flow, the losses. Remember that we have losses of 5 millimeters per hour, right? Remember that we have 5 millimeters per hour. So we need to add everything by wait. Is the area given? No. Wait, how do you add the base flow? How do you add the base flow? Wait, let me think. Because this is still direct runoff. So in actuality, right, you have like this part, which is base flow. Any of you remember? Hey, whoops. Base flow is negligible. Okay. Thanks. Thanks for reminding me. Never mind. You just need the run off. Okay. Because in actuality, right, you need to add the base flow because the one that we are considering is only direct runoff. So we need to add our final results with the base flow. But since base flow is negligible, then we don't need to add. Okay. So again, let's go back. We just need to add horizontally because graphically, right, we're adding the coordinates of this with coordinates of this. We add them together, we get the new coordinate. In tables, we just add horizontally. So 0, 86.7, 144, 206.4. Then we add this one. So 130.8 plus 43.35, 174.15. Okay, I'll make it 2 lah. I'll round it up. 98.7 plus 72, that's 170.10. 7, sorry, 17. 103.2 plus 36.3. 139.5. Then 65.4 plus 25.2. 90.6. So this is 49.35. 18.15. 12.6. And at last, 0. So we are done with the question. So it's just about what's that? Yeah, it's just about, yeah, it's just tedious. It's not hard. So I think, right, if you, I think it's better to study hydrology first. If you're confident, you can do the hydraulics. But oh, that took like 30 minutes for B1 and B2. Okay, so this one, right, I will skip because I mean this is the same exact question. So I'll just go to flood routing. I guess after flood routing, if you guys are still strong, it's almost 4 hours. So if you guys are still strong, then I will do the river also. I mean the river discharge. If you guys are tired, then I guess I'll end it. We see how. Okay, so let's go to flood routing. Okay, so we have storage elevation. Okay, so I think this is a new topic, so I'll go a very, very, very brief run. So reservoir routing, right? So to find, okay, so we need this. You remember there's this table, right, with this formula, but then you need this table. To get this table, you need it from this thing. Okay, I'm not making sense. Okay, okay, basically, right? Um, for reservoir routing, we need outflow storage relationship because for reservoir routing, storage is a function of Q. So we are interested the relationship between Q and storage. So how to find it? So in real life, you have storage elevation relation. So how do you find it? Using contours. I won't go through this exactly because from the past papers that I've seen, there's none. So, but this is like in real life. Like in real life, you find the storage elevation using contours. Then you find the relation of outflow and elevation. So it depends on the question. Is it so like let's say we have a dam, right? We have a dam. This is water. So our outflow, right? It depends on how does it flow out. Weir flow means it flows over. So the one you remember the spillway, the one from hydraulics. Yeah, this is weir flow. So the equation is Q equals this one. Then we have pipe flow. Pipe flow means like in the middle you have like a pipe, and the pipe is fully, what's it? It's fully filled with water. Then you use this one. But then if it's not fully filled with water, it's called the orifice flow. It's only partially filled with water. It's an orifice flow. But anyways, the formula is the same, so it's not really important. Okay, so basically, right, the story is once you know the storage elevation relation, you know the outflow elevation, because both have elevation, right? So you can combine these two equations and get the outflow storage, the one that we want. Okay, I mean that's the full story. Yeah, but usually it's already given in the form of table or equation, so you don't need to do all this. Okay, sometimes you need to do this, but usually this one you don't need. Yeah, but basically in real life you need to find storage elevation, outflow elevation. You combine the two equations, you get the relation of outflow and storage. That's in real life. Okay, so let's go to the flood routing. So okay, so the proper name for it is actually the modified pulse method. I think Pulse is the one who made the method. So yeah. Okay, so again, for this one, right, I won't go through like explaining this. I will just directly do questions so it's clear. Okay, but you need to prepare two tables, sometimes one, sometimes two, depends on the question. So this is the output that we want. So basically, right, we know let's say we have a reservoir with a reservoir. This is inflow, this is outflow. So usually, right, we know the inflow. So we know the inflow. We are interested in the outflow. So yeah, so that's why you need this table. Just remember the headings. Then you need this table. This table is the one that I explained before. It's this one. It's from this one. So the second table relates outflow and storage. Yeah, and then this is the two important equations. I think it's given, so you don't need to die memorize, but I think it's better to memorize just in case. And then that's reservoir routing. We also have channel routing, which is another method. You have this equation you need to memorize, not memorize, as in like understand. So for channel routing, right? Okay, actually, let me draw. So for storage, right? Sorry, this reservoir. We have this. So this is reservoir. We are given inflow. We do not outflow. Okay. So for channel routing, it's a bit different. I think I'll draw it here because I have space here. So for channel routing, it's basically saying like this. Let's say you have a channel. Let's refer to hydraulics. Let's say mild slope and I don't know, mild and steep slope. So they have like different conditions. Okay, they have different conditions. So let's say you have rain. So for each section have their inflow and outflow hydrographs. Okay, so for each section they have their inflow and outflow hydrographs. Okay, wait, let me draw this like this. So you can characterize each channel by, firstly is called the K, and secondly is the X. K is the distance between, like the time between the inflow and outflow hydrograph. It's like approximate. Okay, it's the time between the centroid of the inflow and the outflow hydrograph, but it's approximately the time between the two peaks. Okay, so this is K1. This is K2. So, and X is, what is X? X means it's the weighting factor. So, as in, it's just saying which is more important inside this channel. Is it the inflow more important or is it the outflow more important? So that's what X is. So for each channel, they have inflow, they have outflow hydrograph, they have K, they have X. Okay, but usually we can assume this outflow is the inflow hydrograph of the second channel. Okay, so usually, right, we are interested in either one, we are interested in finding K and X of the channel. So we can characterize the channel with K and X. Sometimes that's what we are trying to do. The second thing that we are trying to do is find this outflow hydrograph of the second one. So given the channel, find the outflow of the other section. Okay, so there are two things that they can ask. So the first one is the first one is finding K and X. So given a channel, you have the inflow and outflow hydrograph. Find K and X. So characterize the channel with K and X. So how do you find it? It's called, okay, there's actually no method to call it. Basically, you plot this. So this is your inflow hydrograph. This is your outflow hydrograph. X is the weighting factor. It's the one that you want to find. K is, again, it's the one that you want to find also. S is the storage. So these are the steps. So workout storage, assume X, plot storage. I think I'm going too fast, but I mean, you can read this inside your lecture notes. I'm just reviewing. Okay, so again, the context is you are given inflow and outflow hydrograph of a channel. Okay, so this is the inflow hydrograph. This is the outflow hydrograph. You want to find the K and X. But to find K and X, you need storage. So you need to find storage first. So you average the inflow and outflow, average the inflow and outflow, like for each, as in like for each timing, as in you find the change in storage. Change in storage is basically just inflow minus outflow times time. This one. Okay. Logically lah, if you have a storage, of course inflow means adding storage. That's why positive I. Outflow means losing storage, so minus Q. But then I and Q is in meters cube per second. So you need to times time to convert it to volume. Yeah, and then you assume storage equals 0 in the beginning. Oh, sorry, 0 in the beginning. Yeah, assume 0. Then you add 91, becomes 91, and yeah, do this. Okay, then you just plot. Sorry. Oh, so you just plot. This thing to storage. Okay, so different. So you must assume X value. So sometimes X value will have like a loop this big. and then like this small, this small. You trial and error until you have x value that approximately makes the graph into a line. Yeah, and then k just equals 1 over slope because yeah, just rearrange. So s is this one, right? Which is the run over, and this one is the rise. So yeah, it's 1 over slope basically. So that's finding k and x for a channel. The second part is, again, this is the second context of predicting this Q2. So given the first channel, find Q2 of the second channel. Okay. Yeah. So yeah, I will show you how to do this, but basically, right, you are given inflow. Inflow is, wait a second. Yeah, inflow is this one, this inflow. Then you have C0, C1, C2. So C0, K is K2, by the way. K is K2, X is X2. So you use the K and X of the channel of interest. What's delta T? Delta T is the time increment. So let's go back to the hydrograph. This is delta T. Delta T is the time between the two inflow and outflow point. Yeah, that's delta T. What else do I need to say? Yeah, I2 is okay. Let's do the question. I think it's clear. Okay, let's go to reservoir routing first. So again, so this is reservoir have outflow storage relationship described. So okay, so this is what I'm saying. So they won't give you the contours, like the contours, and you need to find the volume, and then you need to find what the weir flow. No need. Sometimes it's directly given. It's either in the form of table or in the form of equation like this. Okay. Yeah, you have that. Where S is reservoir storage, 10 to the third, and Q is reservoir outflow. Table for C is inflow hydrograph into the reservoir. So outflow at time 0 is 5. Determine the outflow hydrograph. So this is our reservoir routing. This is the modified pulse method. So what do you need to do? You construct the graph. Okay, some more tedious questions. So time in hours. You have inflow. You have 2s divided by delta t minus, is it minus first or plus first? It's minus first, yeah. Minus 2s over delta t plus q. You have q. So set up this thing. You must remember. This one you must remember. It's not given. So 0, 1, 2, 3, 4, 5. Inflow is 5, 20, 40, 90, 60, 15. So Q at time 0 is 5. Okay, so first step, you need to find this thing from this thing. So you need to find this thing, right? So you need to use the equation. So oh yeah, by the way, be careful with the units. Be careful with the units. Okay, be careful with the units. So we have S over 1.8 minus 1 equals Q 2Q minus 1. Um, so okay, I'll rearrange this equation. So I think it's nicer. So 1.8Q 2Q minus 1 plus 1.8. I'm just rearranging the equation so it's nicer. Okay, so this is your storage and Q relationship. So 2s over delta t equals to what? Our delta t is 1 hour, right? 1 hour. So wait, wait a second. Let me think. So the hard part about this is just the units. I'm afraid with the units. That's why I'm still thinking. Wait, wait a second. Um, 2s over delta t. S is meters cubed. T is okay. Found it. So okay, so just to be safe, right? I think we should convert everything to hours and meters cubed. Okay. So remember that S is in 10 to the third. Okay, 10 to the third meters cubed. I think it's better if we convert it to um, meters cubed. So this is S divided by 1000, right? Yeah. So this is in meters cubed already. 1.8 Q 2Q minus 1. 1.8. Okay. What else do we need? So we need 2S delta T plus Q, right? So 2S over delta T. Oh, wow, this is very complicated. Wait. Okay. So delta T is delta T is how much? 1 hour, right? So 3600, right? Anyone confused? Anyone confused? So this is changed to SI units. This is changed to SI units because our storage is in 10 to the thirds, right? I want to convert it to meters cube. So that's why I divide by 1000, right? Wait. Whew, phew, phew, phew. Yeah. Um. Okay. And then we have T, right? We have T, which is 1 hour, right? This is delta T. This is delta T, which is 1 hour. That's why 3600. Why S divided one? It's given. It's given. It's given. It's given. It's given. So this is the. So okay. So in the tutorials, right? Yeah. No, no. It's used. Okay. Okay. Yeah. This question only. But if you see, right, usually they either ask you to construct the table or they give you the equation. Okay. Yeah. But for this question only, you are given the equation. So you need to. Yeah. Yeah. You get what it means, right? Okay. So okay. So 2s over delta t is just 0.5 q, right? 0.5 q, 2q minus 1 plus 0.5. So 2s over delta t plus q is, so you add q to this thing. So 0.5 q, 2q minus 1 plus 0.5 plus q. Okay, so now you have q equals 5. So you put it here. You put it to this thing. Okay, so how much is that? So, okay, this is one of the more tedious ones also. So 0.5, what's okay, honestly, right? I'm not sure if I'm right, but like based on okay, at first I need to see the answer key actually. I'm just wondering how they do this because this is how I would do it. So 10 minus 1 plus 0.5 plus 5, 28. Okay, so we have 28, right? So what's our next step? Our next step is to have this one. So how do you have that one? You use this equation. So 28 minus 2 times 5. So that's 18, right? It is 18. It is 18. Okay, so what's next? From this thing, you need to find this one. Thanks for pointing out. I forgot to times 2. Thanks. Okay, so I forgot the times 2, guys. So this is about 3,600. Sorry. Okay, this S over 1,000, right? So if you want to make it 2S, multiply by 2, so it's 3,600. Oh, no, it's very nice. Oh, Q 2Q minus 1 plus 1. So Q 2Q minus 1 plus 1. Okay, sorry, some technical difficulties. Okay, so this one, go to, firstly, go this one. So 5, 10 minus 1 plus 1. So that's 46. Okay, so first step done. Next up, you need to find this one from this equation. So you have 46 minus 2 times Q, that's 36. Step 3, you need to you need to find this one. How do you find this one? You use the first equation. So you have I1 plus I2 plus that much. So I1 is this one. I1 is the current row. Okay, this is current row. This is current row. This is next row. Yeah, this current row. Basically subscript 1 means current row. Subscript 2. Did you forget plus Q at the bottom of the equation? Okay. Okay, thanks, Dennis. Break. Okay. 5, 2 times 5 minus 1 plus 1 plus 5. So 45 plus 1 plus 5, so plus 6, 51. 51, sorry guys. 51. Okay, so you need to find this one. So 51 minus 2Q, that's, sorry, this is 5, this is 51. 51 minus 2Q, so minus 10, 41. Then you use this equation to find this. It's been 4 hours. Okay. Okay, guys. Mental breakdowns. Yeah. Okay, never mind. I can finish this. Okay. So we use I1 plus I2. So that's 5 plus 20 plus this thing. No, plus this thing, 41. So that's 66, right? 66. Yeah, it is 66. Okay, from 66, you can find Q. So you need to sub this thing. So this is 66 equals this thing, which is actually I might want to rearrange this thing also. Wait, yeah. 2s over delta t plus q equals 2q squared minus q plus 1 plus q. So this is 2q squared. Actually, let me draw a line. 2q squared minus 2s over delta t plus q minus 1, right? Equals 0. So use this equation. Yeah, so to find q from this thing, you use this equation. So yeah, your calculators. So yeah. So let's solve it. So mode polynomial degree 2. So you have 2 times q squared. So 2 times q squared. And then you have the b is 0. Whoa, what the heck? Then c is negative 66. So wait, so negative 66 minus 1, right? So you get x1, what's x2? 5.78. Yeah, so that's your q. Okay, so we repeat the process. so so now you have these two, right? You need to find these things. So you use this formula. So 66 minus 2 times 5.789. So yeah, that's okay. Okay, never mind. I won't use the screen calculator. It's very slow. 66 minus 2 times 5.789. So we have 54.422. Okay, so next step, we need to find this thing. So use this formula. So I1 plus I2 plus this thing. So I1 is 20, I2 is 40. So 20 plus 40 plus this number. So how much is that? 114.42. Okay, we need to find Q. How do you find Q? From this equation. So you go back. Yeah, so this is just some tedious freak. So 20 negative 115.42. Okay, so we get 7.59. So again, we find this one. How? From this thing. So 114.42 minus 2 times Q. So we've gotten 99.226. Okay, again, we find this part. I1 plus I2, this one, I1 plus I2 plus that thing. So 40 plus 90 plus 99.226. So we get 229.23. Again, we input this formula. So 5, 3. 12.23 minus 1. 10 point. Oh yeah, check if you get the same answer because I'm afraid that I made an error somewhere. Which is, I'm pretty sure I made an error somewhere already, but let's see. Okay, again, we find this one. You use this formula. So you input this one to this one, then 2 times 10, yeah, that thing. So 207.772. So again, you need to find this thing. So you need to use the first formula. So I1 plus I2 plus that thing. So I1 plus I2 plus this thing. 90 plus 60 plus 207.772. 357.772. So you need to find this thing from the formula below. So 2 negative 357.772 minus 1. You get 13,394. Okay, find this one from what? From this formula. So 357.772 minus 2 times 13.394. 357.774 minus 2 times 13.394. Yeah, that's the thing. It's like, I wonder if we have, was it error carry forward? Because I'm also afraid. And it takes a long, long time to solve this. Okay, then we just need to, the last one, let's go guys. Almost there. We're almost there. Okay, negative 405.986 minus 1. 14.265. Whoa, okay. Done. Oh gosh, okay. So that's our final answer. So 8 marks. So this is, so you can either choose the hydraulics one, the one with the hydraulic jump, or do you want to choose this table? Woodby is not good. Woodby is not good. Oh, okay, so this one done. So let's go to the masking method. So we have, so this context is finding K and X, right? Is it? Let's check. Sorry, let's zoom a bit. So given inflow and outflow, found that, they found that X equals 0.30 and the relationship is this one. So you need to, okay, outflow is how much? 60 find, okay, 60 at time 0. Find the hydrograph at the downstream end of the channel. How do you do this? I see now. Okay. Okay, so someone asked, we don't need to find the Q to S 2S over T plus Q table and then find the outflow using interpolation. Yes, we can use the what's that? Okay, so it depends on the question. Okay, so somebody asked, so in our tutorial, right, if you notice, right, we are given the table. So we are given Q S, we can find 2S over delta T plus Q, right? Then we just use linear interpolation. um Honestly, I'm not sure, but I think in my perspective, you really must use the formula directly because it's more accurate. Yeah. um yeah, actually I'm not sure about this one, so yeah, but then it depends on the question, because sometimes, right, sometimes, okay, I'll show you. Okay, let's leave this for a bit, let's see this one. Derive the storage discharge table. See, sometimes you are required to find the table based on this one. See, this is discharge to the overflow spillway. So yeah, so sometimes they ask you to make the table, sometimes they need to use the formula directly. I'm not really sure, maybe you can ask the prof about this, because yeah, because like from what I know, right, you need to use the formula directly. Yeah. Okay, let's go back. So this case, right, what's this? Okay, so this context is you're given a river, right? So you know the inflow, you know the inflow is very, very big. Okay, you know a river, you know the inflow hydrograph, you know the outflow hydrograph. Okay, sorry, you don't know the outflow hydrograph. Then so you need to find the outflow hydrograph. You're not given. You need to find the outflow hydrograph. You have K, you don't know X, but you are given this. Okay, so sorry, X is given. X is given. So you don't know K, but X is given. So let's just, okay, so first we need to find K. How do you find K? Of course, using this graph. So again, if you remember, right, S equals K times this whole thing, which is X times I plus 1 minus X times Q. So K is basically S over the thing, right? So it's 1 over slope. So let's find the slope. So the slope is, let's pick 2 points. This point seems nice. Which else is nice? This point seems nice. Okay. So we can use this. So slope, right? Rise over run. So rise is 550 minus 150, all divided by 50 minus 10. So how much is that? 10. Okay. 1 over 10. Sorry, 0.1. So 0.1 is the storage constant, which is, be careful with the units. This is in 10 to the 6 meters cube. This is in the meters cube per second. It's always check units. It's very important. So I think so storage is this one, right? It's times 10 to the 6. Okay. So this is, okay, let me do it again. So 40 to the negative, so to the 6. We have 100,000 seconds, okay? Seconds. Because again, this is in meters cube, this is in meters cube per second. What else do we need to find? Oh, you need to find the Q, right? We need to find the Q. So you need to find the equation, this thing. So C0, C1, and C2. So let's find C0. Wait, so let's check delta T. Delta T is in days, right? Delta T is in days. So your units, right? Your delta T and K should be consistent. So in this case, right, I think it's convenient to use days. So how many days is this? So 100,000 divided by 24 hours. So 3600. So how much is this? Okay, so our K is 1.1574 days. So we calculate C0, C1, and C2. So C0 is negative. K, which is 1.1574. What's X? X is 0.03, 0.3, 0.3. Sorry. Minus 0.5. Delta T is 1. K is... Okay, you get my point. Okay, you find C0, C1, and C2. Okay, I won't go to the calculations. It's just very long. I'll just directly calculate it in my calculator. Okay, so you have 0.1166. Oh yeah, be careful by the way, guys. Not be careful, sorry. The bottom one is always the same. So when you put in your calculator, right, you don't need to erase everything. Yeah. Don't erase everything. It will just take up too much of your time. So this is 0.6. C2 is 'What's K is 1.1574. Okay, so you've gotten these T values. Okay, how do you check that these values are right? Sorry. Okay, sorry. How do you check these values right? You check C0 plus C1 plus C2. Let's see how much we get. Plus 0.6466 plus 0.2367. So we get 1. So if it's 1, then you're correct. Okay. This is just to check. Just to check if your calculations are correct or wrong. So C0, C1, C2 done. So let's proceed to our table. To the Muskingum method. I don't know how to pronounce it actually. Muskingum. Okay. So let's proceed. New page. I don't have enough space. Okay. So what do we need for the table? We need time I C0 C0I2 C1I1 C2I and C2Q1. Am I correct? I might be wrong. I am correct. Yay. Okay, so it's this one. Q2 equals C01I2 C1I1 C2Q1. Okay. C0I2 C1I1 C2Q1. So the final column is Q. This is in meters cube per second. Okay, so you've gotten this. So let's construct the queue. So 0, 1, 2. But actually, how long do we need? 6, right? 0, 1, 2, 3, 4, 5, 6. Okay, so the I, right? Uh, Let me take a picture. I don't want to scroll back and forth. Okay. Okay. So that's cool. So this is 60, 100, 350, 600, 360, 250, 120. Okay, let's go with C's. Okay, let's go with the method. So Q, I need to scroll up. Shoot. So start with what? Q equals 60, right? Q equals 60. So let's start with Q equals 60. Okay, so how do you do this? Where's my C0 and C? Okay, copy and paste. Just so you've gotten these three values, right? Okay, you've gotten these three values. Now you just need to apply it. So again, it's C0 I2, C1 I1, C what? C2 Q1. Okay. So I1 is the again, I1 is the current row. So okay, so our current row is row 0, right? So we input this, and this. So these three are what we're finding. Okay. So let's find C0 I2. So C0 I2 is just 0.1166 times 100. So 0.1166 times 100. That's 11.66. C1 I1, that means that we multiply C1 with 60. So 0.6466 times 60. 38.796. I'll use an exact number, I guess. Then for C2, right? C2 is 0.2367. 0.2367 multiplied by Q1, which is 60. Okay, so 1 is the current row, 2 is the next row. We have 14.202. So how do you get Q2? You add up everything. You add up everything. So yeah, you add up everything. 796. Yeah, this is a very repetitive process. So 64.658. Again, you just repeat the process. So you're aiming for these three. So C0I2, so 0.1166 times the current, oh no, I2 is the next one. I2 is the next one. I2 is the next one. So it's 350. So 40.81. Then C1 is 0.6466 times 100. Then C2 is just 0.2367 times Q1, which is this one. Which is 15.305. Then you add up everything. 120.775, and then you repeat the process again. um, can I use Excel for this? How? Actually, okay. Actually, no Excel, no Excel. I must stay true the. Was that? Imagine this is like the real test, so yeah, no Excel. I'm very tempted, but I don't think so. So C0 is 0.1166 times I2 is the next one, so it's 360. C1 I1, so it's 0.6466 times I1 is the current I, so times 600. Then C2 is 0.2367 multiplied by the current Q. Am I doing this wrong? I might do this wrong. Crap. Oh no. I think I might have wrong input somewhere. Oh no. No. Is it correct? Oh no. Okay, so these three, right? These three, let's go to these three. So C0, so 0116 times, what's I2? I2 is 600, right? Yeah. So 69.96. No, because sometimes I forget that I1 is the current row. The current row is this one. The current row is the one that we have all information on. So I2 is 600. I might have forgotten it somewhere, but let's see lah. So I1 is 350, right? So times 350. Then C2 times Q1. C2 is 0.2367 times Q1 is 120,775. Okay, so you add up everything. 324.857. Okay, so let's go to the next one. So C0 is 0.1166 multiplied by I2. So it's 360, right? Divided by 360, 41.976. Then C1 is 0.6466 multiplied by I1, which is 600, 387.96. C2 is 0.2367 times Q1 is 324. So again, add up everything. 506.83. Okay, we're almost done. We're almost there. What's I2? I2 is 250. So 29.15. Then C1 is 0.6466. You multiply by I1, 360. So this is 232.776. C2 is 0.2367. We'll multiply by Q1. So 506.83. It's 119.966. 39.15 plus 32.76. So you get 381.893. Almost done. Last one, last one, last one. So 0.1166 times I2. What's I2? 120. 13.992. C1 is 0.6466. So multiply by I1, 250. Then C2 is 0.2367. You multiply by Q1, which is 381. So it's 90.394. So you add up everything. 13.992, 761.65, 9394. So it's the last one is 266.036. Yes, your final answer. Final done. Okay, so how do you check your final answer is right? It must be how do you pronounce this one? Attenuated. This I don't know this word basically, and lagged. Attenuated. Okay, something like that. Attenuated and lagged. So if you see, right, the I, right, 600 is here. For the Q, it's here. So again, it's lagged. So it's nice and it's not as high. So your answer is probably correct. So yeah, that's how you check. So yeah, I hope this one is clear. I think it's everything for hydrology. I mean, besides the river, but the river, I think you can read yourself. Okay. So yeah, this is the same question. You just need to find this one. I think I'll show you later. As in, like, I will do it off camera. I'll just send the send the solution, I guess. This one is the same as before, the one with C0, C1, and C2. So yeah, okay. So I guess at this point, okay, any questions? Either from hydrology and hydraulics, both can. I think we've done a lot for today, like a lot. So yeah, so I think we can, yeah. So we scroll up, I guess. So this is the, what's that? This is the Muskingum method. Yeah, this is the reservoir routing. Yeah. So yeah, are you guys still there actually? I'm just wondering. I know some of you are still there, which is amazing. It's like been almost 5 hours. What the heck? I didn't expect this actually. So yeah. So this is the predicting hydrograph. Why is it piece flu? It's not piece flu. Let me change. So please predicted hydrograph. The no piece flu. Yeah. So yeah, honestly, I was expecting 3 hours, at most 4. I didn't expect 5. Oh wow. Yeah. So yeah, again, this is like, I hope this is helpful, especially on the hydraulics. Yes, this one will have recording. I will send to the group. Yeah, so yeah, I guess like this is like one last scroll. So you guys can, yeah, you guys can like stop me anywhere. Yeah, I know. Like even me, I made like a lot of mistakes. Okay. But yeah, so if you see that there's like a lot of blank questions for you to practice. I mean, this is like already by topic, so I think it's nice. Yeah, especially the hydraulics. Yeah, so yeah, so any questions, especially this part too, especially this part, like the combo questions. You really you because I think all hydraulic questions is combo questions mostly. Yeah, this thing. The PYP questions in this review cost collusion. For hydrology, I have the solution from my senior, so you guys can refer from that. It's mostly correct from what I've checked. Yeah, from Ryan. For the hydraulics, just stick to 17, 18. The solution is very nice, and I see that it's quite accurate. Do not see the 15, 16. I think that's the first one that I saw. Wow, that one is very bad. I think not very bad. I think like this is supposed to be Y conjunction, right? Yeah, conjugate depth, right? I think she or he used critical depth, which is totally wrong. Okay, so yeah, so I said like when you see the hydraulics past papers, the solution, be wise because I know some of them are not accurate. So yeah, so for hydraulics, just go to 17, 18. Yeah, this one is the graphing. Yeah, I think for hydraulics, you can start from the graphing first. I think it's the most important part, I guess. Yeah. So yeah, I have the solution like this. I can send it to you now. So are there any questions? Or already break down everyone? Tired? Oh my gosh. Okay then. I guess if no question, then I guess I'll send this to the group. I'll send the recording, and yeah, good luck for your studies, especially with the back to back finals. Yeah, so this is the one that I messed up. Okay, so this is, what's this? Oh, this is the energy. Choking. Yeah, this is choking. Yeah, this is the specific energy. This is the uniform flow. And then yeah. Okay, so that's everything. Okay, in that case, if no questions, yeah, I guess that's everything. So I hope you guys all get a good score lah. Yeah, and rest well. So thank you everyone. I'll stop recording now.